Madam, please start, madam. Nogratna, madam.
Okay.
Okay.
Good morning, one and all. I am Nukaratnam, head of the Department of Geology, Adikavi Nannaya University. It's my privilege to welcome today's keynote speaker, Sri C.V. Rao, Executive General Manager, ONGC, and speakers of today's webinar, Dr. Nimisha Vedanti, Senior Principal Scientist from NJRA Hyderabad, and Dr. Satyavani, Principal Scientist, NGRA from Hyderabad. Convener of the webinar, Dr. K.V. Swami, Dean Academic Affairs, Faculty of Sciences, and Professor Y. Srinivas Rao, Department of Geology, and AC members of the university, deans, directors, faculty members, dear participants, who are present over here, a warm welcome to you all for today's webinar on unconventional energy resource, Indian scenario, being organized by Students Chapter, Society of Petroleum Geophysicists, and Department of Geology, Adikavi Nannaya University. First of all, my sincere thanks to Honorable Vice Chancellor Sir, Professor Mokka Jagannath Rao Garu, for constant support and encouraging us to conduct this webinar. Also, I would like to thank keynote speaker Sir C.V. Rao and speaker Dr. Nimisha Vedanti and Dr. Satyavani for accepting our invitation. As our country is at the cusp of huge energy demand, it is very important to throw more light on unconventional energy resource, which has high potential to give the energy security in the times to come. I'm sure that today's webinar topics are going to immensely benefit to the students of geology, geophysics, and research scholars, faculty members, and participants to a great extent. And today is the birth anniversary of Pingali Venkaya. Today's 12th August has birth anniversary. We all should remember who is a designer of our national flag. And with these few words, I now request Dr. K.V. Swami, convener of the webinar, to give opening remarks.
Thank you, Dr. Nogaratnam, Madam, Head of the Department of Geology. Good morning to all. It's my pleasure to present this convener's report today. Before presenting my convener's report, just one thing I am to share with you all that actually today's webinar is to be attended by our Vice Chancellor Mokka Jagannath Rao, Registrar, and our Principal, Registrar, our Professor T. Ashok, and our Principal, Dr. K. Ramaneshwari, Madam. But because of some urgent official commitments, they have to leave the campus to attend some meetings elsewhere. So they could not attend this particular webinar. And now, as being the convener of this particular today's webinar, and also as a faculty advisor to Students Chapter, SPG Students Chapter of our university, I welcome all the dignitaries to this webinar on conventional energy resources, particularly Sri C. Visweswar Rao, and Dr. Nimisha Vedanti, and Dr. N. Satyavani. And really, I am very thankful to them. Immediately when I approached them, just as sir or madam, I am planning to, our students of chapter is planning to organize one webinar on unconventional energy resources on so and so day. They readily agreed without saying no or anything. And for that, I am very much thankful to them. And this actually coming to this particular our university, because some of these speakers do not know the history of our university. Our university, Arkavan Anna University, was established in the year April 2006 by an act of Andhra Pradesh Legislative Assembly. And this particular, our university offers MSc Geology program of 2 years duration with a specialization in petroleum exploration since the academic year 2012-13, and MSc Geophysics again is of 2 year duration from the academic year 2017 and 18. The student chapter of SPG was established in our university in the year 2018. Actually, in the same year, a couple of our students, geophysics students, got the opportunity to participate in the national symposium of SPG that was held at Jaipur during November-December 2018. That is the first year in which our SPG students chapter was established in the year, and continuously then since then we are organizing several programs, particularly for the benefit of students. But guest lectures on well logging and seismic methods are different geophysical techniques. But we could not organize any academical program in the year 2020, March from 2020 to till date, because of the COVID pandemic situation. And coming to this particular today's webinar, we know that for many decades, conventional hydrocarbon oil and gas reserves, which could be produced at low cost, was present in abundance. However, also we know that it is clear that we are gradually running out of these conventional hydrocarbon reserves, particularly which could be produced at low cost, meeting the strict environmental standards, and also new sedimentary basins to explore for these reserves. So that is why I thought a webinar like this could be organized for the benefit of the students by this particular SPG students chapter, and that's why this particular webinar is planned. And also we know that major oil companies, because of the depleting reserves of the conventional energy sources, major oil companies in the world and also major energy consuming economies, including China, USA, India, and Japan, are now looking for the investments in the exploration of and the production of unconventional hydrocarbon energy resources like oil shales, heavy oils, tar sands, shale gas, coal bed methane, and gas hydrates. But the knowledge about the geological setup under which these unconventional hydrocarbon resources are accumulated, the strategies to be adopted in their exploration, their estimates, and the technological developments in their production, etc., are still at an early stage, at least at the student level. Maybe at higher levels, the knowledge about these things may be known to several scientists who are involved in these aspects, and also oil companies. But at the student level, as far as my knowledge is concerned, this knowledge about these things is very limited. Hence, a series of academic programs have been planned and arranged by our SPG students chapter on unconventional hydrocarbon energy resources, through which student community will be benefited and gain the knowledge about these resources. So today's webinar is the second program in that particular series. The first one being the guest lecture delivered by Sri T. Ram Prasad, retired chief scientist from National Institute of Oceanography, Goa, on gas hydrates on 2nd July 2021. So with this brief report about the convener's report, I thank you one and all once again for participating in the seminar, and also I thank once again all the speakers for accepting our request. So thank you. I hand over mic to our head of the department once again.
Thank you, sir. Thank you for valuable remarks. I now request Hello.
Hello, madam, please continue. Webmaster, please unmute Dr. Lokaratnam, madam. Okay, madam, unmuted. You can continue.
Madam, your network bandwidth is very low, madam. That's why.
Hello. Srinivas
Hello.
Rao.
Now okay, now okay. So, madam, voice was మాట్లాడండి madam.
Hello.
Okay, madam. Okay, fine. Audible, madam. Please continue.
Sam sir, here's some problem. You continue.
Madam, we could
Please
we
go
could
on.
hear your voice. We could hear your voice. Please continue.
One second. I now request. Hello. Okay. I now request one of the student from geophysics to introduce our keynote speaker, Shri C.V. Rao. Hello. Sir, one second, sir. Before your speech, the student will introduce.
Hello.
Sir.
Hello.
Rutu will introduce, sir. Will introduce. Now I invite Rutu to introduce our keynote speaker, C.V. Rao. Over to Rutu.
Okay, ma'am. Good morning to all. I introduce myself, Mantena Rutu, as a student of final MSc Geophysics program of Adikavi Nanna University. It is a great pleasure for me to introduce today's keynote speaker, Sri Choppal Vishweshwar Rao. Sri Vishweshwar Rao sir completed his MSc Tech Geophysics from Andhra University and later PG diplomas in Applied Statistics and Personal Management. He is currently pursuing PhD in IIT Mumbai. He joined ONGC in 1983 at CSD Sri Keshwadeva Malviya Institute of Petroleum Exploration, Dehradun. Prior to joining ONGC, he served Geological Survey of India and got experience in conducting gravity, magnetic, self-potential and induced potential and thermal surveys. Sri Rao sir is one of the very few experienced persons available in seismic application programming interface and quality control in both offshore and onshore. He was experienced in a deep water control group and related quality monitoring jobs. He was in exploration and development departments in Dehradun, Krishna, Godavari and Kaveri basins for 3 years. He served as head geophysical services of ONGC in Dehradun and got experience in a national seismic APA project as in charge. Sri Rao sir got experience in quality control of acquisition and processing with various companies onshore and offshore. He was associated in Pan India reprocessing quality control with various companies. He was also associated in benchmarking project of NGRA, onboard processing and interpretation systems, long offset benchmarking project, bathymetric engineering, management migration, geotomo and common reflection angle migration quality control. He was and expert in dealing with imaging issues of sub-basalt basement, 3D, 3C, node and multi-components. He is an active member of Society of Exploration Geophysics, Society of Petroleum Geophysics, Indian Geophysical Union, India Science Congress, and Application of Environmental Geological, and served as Vice President of SPG India for 2 successful terms. Published and presented several technical papers at national and international levels as an author and co-author. Delivered a number of talks on seismic to the students in various universities and other knowledge sharing platforms. He has a passion to get updated in subject and to put up hard work in every job taken up for its successful and timely completion. Thank you for giving me this opportunity. Now I request to deliver Sri Vishweshwar Rao to deliver her lecture. Thank you for giving me this opportunity.
Thank you, Ms. Rutu. Thank you for giving me the opportunity to present as a keynote on this. I thank SPG student chapter of AKNU and Department of Geology, AKNU. I respectfully vote to Vice Chancellor, Chief Patron Jagannath Rao Garu, and Patron Registrar Professor Ashok, and co-patron and principal Dr. Ramneshwari, convener Dr. Swami Garu, co-convener Dr. Nokratman Garu, eminent scholars from NGRI, Dr. Nimisha Vedanti and Dr. N. Satyavani. Incidentally, I know both of them from SPG onwards. Friends from Oil India, QSAT, ONGC, IIT Bombay, who joined this webinar, and students of AKNU. Thank you so much for giving the opportunity. And now I start my talk on this. I'll share the screen hereafter. Are you able to see the screen?
Yes, sir. Yes, sir.
Okay. Thank you. The talk goes on unconventional hydrocarbons in India. A positive note as a prism, we have put it as a light on the horizon. First of all, it's a very fabulous light for me, which gives complete positivity. Running away from any problem only increases the distance from the solution. The easiest way is to solve the problem. Conventional hydrocarbons, we all know that they are highly porous reservoirs with sufficient permeability to allow gas to flow to the producing well. A pressure regime tends to move the gas towards the producing well. Because of the time constraint, I talk the important, touch upon the important points, whereas the complete notes is for the students to get enriched with the particular idea of unconventionals. I'll share the presentation to the students. Unconventional hydrocarbons normally comes with deposits of natural gas found in impermeable rock formations. And then to produce them, we have to give the artificial pathways, generating the fractures into the subsurface. So the implications will be, we have to understand the subsurface better. We need much higher number of wells and state-of-the-art technology to go into the subsurface, and exactly wherein we have to take the horizontal curve, and then wherein we have to fracture depending on the subsurface scenario. Then unconventional hydrocarbon resources, when we talk, we have oil and gas resources, oil shales, tar sands, heavy oil. And coming to the gas resources, more popular, the clastic or carbonate reservoirs like tight gas and basin-centered gas, and shale coal reservoirs like shale gas, gas hydrates, coal bed methane. And then unconventional hydrocarbon resources are controlled by the evolution of the source rocks and combination of different unconventional reservoirs. They are characterized by tight reservoir properties, non-buoyancy driven migration, and obviously there is no trap boundary. Am I audible? Okay. Widespread micro and nano scale pores and the resistance for high capillary pressure in tight reservoirs and lack of conditions providing the strong buoyancy is the problem. An unconventional petroleum has two key parameters. One is the porosity less than 10%, and the diameter of the pore throats either 1 μm, permeability is less than 1 microdarcy. So unconventional petroleum include, as Swami sir told, tight gas, tight oil and gas, shale oil and gas, and low permeability, heavy oils and all. And here we are from ONGC also, we are trying to talk on unconventional reservoirs, wherein we are adding some more also. I'll come to that later. Unconventional reservoirs will have complex and highly heterogeneous scenario, and they are characterized by low porosity and ultra low permeability. The strong physical and chemical interactions in the fluids, they will lead to the inapplicability of the conventional approaches for fluid to go through the porous reservoir rocks. This is the problem in the unconventional reservoirs. When you talk about the hydrocarbon resources, conventional resources, for them, the dynamic balance process controls the accumulation, and the gas potential controls the accumulation to the structural highs. Whereas coming to the unconventional scenario, the subsurface temperature pressure fields control the gas content, and this effect along with the water potential and pressure accumulation in the synclinal side. So unconventional and conventional hydrocarbons do exist together, and unconventional hydrocarbon has three distribution models. Basically, we found them. One is the intra-source rock model, which is very famous in coal bed methane. Dr. Nimisha will explain in their presentation. So, and then the source rock interlayer model is for the shale gas and other scenarios, and basin-centered gas model is the third one. I try to put how the figures will be in that. The intra-source rock distribution model, and I'll try to cut the pen highlighter. Okay. Intra-source rock distribution model, basically you see that there is only one rock distribution, and whereas interlayer model for the tight gas will have the interlayer connectivity for the source point only, not for the permeability point, whereas basin-centered gas will be in one this thing. These are the three models normally we use. And we talk about the resources. Hydrocarbon, which may or may not be produced in the future, can be called as resources. A resource used to be appraised with the extra seismic survey or additional delineation of the wells to make it to the reserves. So four components constitute the oil gas in place, what we call reserves, resources, amount already produced, and unrecoverable quantities of petroleum. The petroleum reserves are the volumes that will be commercially recovered in future. Depending on the extent of exploration carried out in a particular resource reservoir, there will be three categories we call: proved, probable, and possible. Possible reserves will have 10% being produced. Certainty is 10%. And then by doing more extensive surveys or drilling the wells, we can convert this one to probable reserves, and ultimate is the proved reserves. The industry is now moving towards PRMS, that is called Petroleum Resource Management System, that takes care of all the reserves and then the dynamic process of monetizing the reservoirs right from possible to proved. Then there is another way of calculating the reserves for both conventional and non-conventional. The anticipated reserves which are commercially recovered from known accumulations from a given date, particularly can be called as 1P, 2P, 3P in the field development plan. These reserve, when they talk about 1P, 2P, 3P, you can say that either they are justified projects or they are already in development. Then the main gathering types of oil and gas, both conventional and unconventional, are 4 types: isolated, cluster, quasi-continuous, and continuous. Conventional oil and gas gathering isolated type will be for the structural reservoirs. The word itself says that it's an isolated between the structure. And a cluster type will be a stratigraphic reservoir, and lithological reservoirs will have 4 or 5 clusters wherein we can take care of that. KG 98/2 is one of the biggest examples for taking care of the cluster type of development by ONGC. And unconventional oil and gas will have either quasi-continuous or continuous. Quasi-continuous will be particularly fractured oil and gas. It's either it's a carbonate, volcanic, or metamorphic fractured. The heavy oil and tar also come under the quasi-continuous scenario. Most of the popular ones comes under continuous one in the unconventional, like shale oil gas, coal bed, then biogas, oil shale, gas hydrates, etc. will come under continuous oil and gas gathering scenario. Unconventional reservoirs characterized by low porosity and ultra low permeability, and they have a strong physical interaction between the fluids and pore surfaces, as we have discussed in the earlier slide. They will never allow, they will stop application of conventional approaches for characterizing the fluid through the porous reservoir rocks. Let it be tight gas, basin centered, or any other thing. Then the GNG and geochemical methods needed to characterize the petrophysical properties, fluid transport, and their relationships at multiple scales. We'll discuss about the scales when we discuss seismic, improving the production efficiency. So here I added one more thing. The other reservoirs having the complex and heterogeneous scenario like basement, HPST, subtrapians are also being treated as an unconventional reservoirs based on their exploration criteria and exploitation scenario like HF and horizontal drilling, directional drilling, and all things, and pore pressure studies led us to talk about these reservoirs also under unconventional category. Then unconventional resource potential is very high. People started looking at it when they have extensive production from the conventional ones. Then when we started looking at it, they found that more natural gas in unconventional deposits rather than the conventional ones. Large oil and gas resources estimated to exist in the unconventional deposits. So potential is very high. Then what enables the development of unconventionals? We have the access, technology, and integration. The advantages in unconventional scenario is their large resources and huge potential. And technological developments earlier was the constraint, but now they are in place, maybe at a cost. Disadvantages are high conversion cost and the transportation cost. Particularly, I'm here by putting this, I am mentioning about the gas hydrates, which we have in the deep water scenario of East Coast, wherein the conversion to gas and then bringing back transportation to the land may be the biggest issue, and which includes very high cost on that. On the environmental issues in HF case in particular, tight gas scenarios in Kaveri, we have a lot of issues, particularly in inhabited areas. The problem is very, very high. This is the resource triangle. When we talk about conventional, unconventional, we must refer to this. This gives a complete picture of the unconventional and conventional scenario. High quality, medium quality, the ones will come under conventional up to 1 microdalsy, and 0.1 to 0.0001 MD comes under unconventional. The one which is shown below gives us the complete idea about small volumes and easy to develop are conventional, large volumes and difficult to develop are unconventional, which are having increasing volumes, decreasing permeability, decreasing reservoir quality, and increasing technology. So this is the scenario about the unconventional scenes which we are going to look at. The reservoir permeability range, again, what we have discussed only, it has been given in a different scene in Spencer. He said that near tight gas scenario in the basin centered gas can be looked at, and I think ONGC has looked at these things in Cambay Basin. The importance of unconventional gas has come because the over 32,500 TCF gas has been identified worldwide in the unconventional reservoirs. This is the slide for particularly students who are interested. The Indian sedimentary basins, we have 4 different categories: proven category, identified category, prospective basins, and potentially prospective basins. Our effort always to put all the things to one category above, and then ultimate is bringing them to the proven commercial productivity. We have taken the Vindhyan basin, which was in the category 3 to category 2, after having a lot of success in Jabera, Damo, and Nauta basin fields. And then coming to shale gas, word itself is there. The shale gas is a gas contained within the shale sequences. And then this shale gas is stored in 3 major ways. One is the absorbed gas in the corrosion, similar to the natural gas from the coals what we get. And then the other one is trapped in the pore spaces of the fine-grained sediments interbedded with the shale. And the third one is confined within the fractures in the shale itself. The fundamental aspects of evaluation is generation potential, that is source; storage potential, that is reservoir; production potential, that is productivity. This is, of course, common for all unconventional reservoirs, not only shale. When we talk about shale, we talk about the thermal maturity, which is the key to understand the shale resource capability. And the typical temperature ranges at which oil and gas are generated are shown in the figure, which is coming 60 to 175 for the oil window and 100 to 300 degrees for the gas window. The thermal maturity is a function of, again, the time and temperature. This is the word. Normally, when we talk about shale gas, we should talk about the thermal maturity. I request the students to take care of the terminology points, particularly when we talk the terminology which is being used in any type of discussion is to be noted, because that gives you the anchor points to understand the scenario which we are discussing. The shale gas potential in India is identified in Cambay, KG, Kaveri, Damodar, and thick shale sequences within the requisite shale potential. Here I would like to mention about the Cambay Basin. And then other prospective basins like Bombay, South Cambay, Assam Shelf, Upper Assam Shelf particularly, and then Assam Arakan Fold Belt, Barmer and Jaisalmer basins also have got tested for the shale gas. And the challenges in shale gas, particularly high technology drilling is needed, hydrofracturing techniques is needed. When we talk about hydrofracturing, we should talk about the huge water handling and disposal required for hydrofracturing. This is very challenging in inhabited areas. Kaveri, ONGC has stopped drilling this particular tight gas seams. And then the advantage is existing oil and gas infrastructure, which we have can be utilized to most of the extent. The targeted for oil and gas basins are particularly, they have to obey the Government of India policies and environmental issues. The tight gas reservoirs are ultra low permeability, which will not provide a smooth flow passage. The sub-economic reservoir qualities, that what normally we call them, and then permeability will be less than 0.1. You can see one example here we have given the porosity is there, but the permeability is lost due to chloride platelet developed in the pore space. Then basin-centered gas is characterized by the regionally pervasive accumulations like gas saturated, abnormally pressured, lack a down dip water contact, and have low permeability reservoirs. So these accumulations of basin-centered gas can be a single isolated one, which will be called as sweet spots. They have to be attacked. I have shown in the figure. They have to be attacked with different drilling points, or otherwise a single stacked reservoir for several thousand feet thick. So it can be either quasi-continuous or continuous. What makes the reservoir tight? You see, you can see the conventional reservoir wherein the permeability and porosity both are very clear, and whereas coming to the tight gas, the permeability issues prevail. So effective porosity, viscosity, fluid saturation, and capillary pressure are the main things which can control and tell about the extent of tight gas, and then difficulty in producing that. And generally it is produced after hydraulic fracturing. The tight gas sand reservoirs, as I said, Kaveri, we have Andamadam sandstone, Bhuvanagiri formation, Nanilam area, and Petrozoic Vindhyan reservoir, again Jabera. Dr. Nimisha knows, she worked a lot on that. And we have proved reservoir qualities, tight and compact porosity values from 8 to 10%. The formation porosity lost due to diagenetic compaction and secondary mineral growth. The coal bed methane, actually the definitions have been given in a different fashion, but ultimately the meaning is same. Methane rich gas which emanates from this and due to change in situ pressure conditions, which is known as coal seam methane also. As per Government of India norms, it is the gas contained in coal or bituminous lignite beds under reservoir conditions and extracted from there during CBM operations. That is the Government of India norm. And then basins with CBM potential in India are 44 Gondwana, and then 16 tertiary coal fields are there. The major ones, of course, I try to mention in West Bengal, Odisha, not Odisha, Madhya Pradesh, I think we have, and Assam, Meghalaya, Neyveli, Kaveri, Barmer, Bikaner, and Jammu and Kashmir also there, the tertiary ones. And then the advantage in CBM is we have huge coal reserve base, and we have third largest proven coal reserves and fourth largest producer of coal in the world. And then vast CBM reserves are there from 850 to 8 ECM estimated in Indian coals. So, and then methane constitutes 90% of the total gas content. That natural gas reserves are very, very high in CBM. That's why CBM is very popular and important. And one good thing here is mostly Indian companies are, I think, extracting the coal exploration and exploitation scenario. And the gas hydrates is a crystalline solid consisting of a molecule, gas molecule, usually methane, surrounded by cage of water molecules. The advantage in gas hydrates is the one volume of gas hydrate contains 164 cubic meters of gas. That is huge amount of gas. Once if we can crack it, we get 164 times the amount of molecule gas we can get from the gas hydrate. That is the one which attracts the explorers and exploiting scenario people. But it is not so easy. These are also called clathrates of methane. Gas hydrates were first observed in 1930, but till then the technology has not been developed to make it production oriented or commercialized. In 1970, 74, 70s, people have worked on it. And it's about 1894 TCM amount of gas, prognosticated gas resources have been there in India. And National Gas Hydrate Program was conducted by ONGC and different companies together in offshore KG, Mahanadi, and even Bombay also, they have done some surveys. So then it comes in the bathymetry of 650 to 700 meters and above. That is the problem. As I told, the extraction and the conversion to gas and then bringing to the land is a big problem. So once the commerciality develops, this can give huge potential in gas hydrates. The gas hydrates, particularly biogenic hydrates, is of 90% with microbial activity in the shallow levels of shelf sediment. Thermogenic hydrates, the thermal breakdown of organic material at a greater depth, which is similar to conventional oil and gas. See, as I told, the prognosticated results are very high, and concentration is there. I'm happy that NGRI is also doing a lot of job on that gas hydrates. Then when we talk about gas hydrate, like we talked thermal maturity in shale gas, and when we talk about gas hydrate, we have to talk about the bottom simulating reflector, a reflector that roughly parallels the seafloor, which is caused by the contrast between the overlying gas hydrates and underlying free gas. So the amplitude which is caused by the underlying free gas is being seen as a bottom simulating reflector, which is a marker to identify the gas hydrates. Gas hydrates can occur without a BCR also, but then the controls on its formation are not well understood. And then difficult place when we talk basement, HPST, ultra deep waters, shale, of course, we have discussed this. We call it as a difficult place, putting under unconventional reservoir category by ONGC. This, if you look at this particular one, strategizing the basement exploration and exploitation, you see that the quality of seismic data for basement imaging, reprocessing, CRAN, multi-component, multi-azimuth, many other things in which most of them I have involved in that. Even the basement exploration, we have done all the possible acquisitions, advanced acquisitions and processing scenes. We have tried TTI inversion also. We have tried full azimuth imaging. We have tried RTM, many other things we have tried. Chasing the leads under basement exploration, which we can get. And the red one, I want to clearly focus on that. Drilling high angle horizontal wells for the basement. This is one thing, puts it into the unconventional scenario. And then the reshaping the basement exploration into three different categories: create, harness, and place is the management trend today. And then HPST, it can be for anything, but it is an unconventional scenario. With wells with a bottom hole temperature greater than 150 degrees, that is 300 degrees Fahrenheit, and about 10,000 PSI. And some wells are reaching higher pressure than this one, what we have recommended as HPST. So they went into the ultra HPST scenario about 205 to 2000 PSI. And then even extreme HPST 260 to 35,000 PSI also come to the extreme HPST scenario. So this is one scene how we'll look at it. See how much temperature is there to address the particular PSI. Drilling, evaluation, and then cementing, stimulation, completion, production, artificial lifting, and HF. Everything is to be monitored in a particular chart for HPST. ONGC has got a center of deliveries for coal bed methane, basement, shale gas, gas hydrates. We have gas hydrates RTC center. And then we have HPST, we have another COD at based at Kakinada. So center of deliveries, depending on the unconventionals, have already been taken full care by ONGC, and we are extracting on that. And then coming, okay, we are discussing about the unconventional resources, but wherein seismic can take care of these things. Here I try to put the role of seismic in unconventional place. The afferent geological, petrophysical, and rock physical analysis are to be done for the use, and the seismic attributes to predict the key reservoir properties. Drilling and completion decisions, ONGC has done seismic guided drilling in Andaman case, and we have done LWD and seismic while drilling. We have seen in this, and we could estimate the fault which is coming up, and wherein we can change the drill bits, saved a lot of money and time for us. that is the impact of risk reduction in that particular scenario. Seismic has helped a lot. Major component of the workflow is acquisition processing of multi-component, full azimuth, long offset, many new technologies which are coming in that scenario. Even the processing also, we have got excellent techniques now. And then microseismics is one thing which is to be which is becoming popular and which is to be more popular than what we are using today. Microseismics is very much required for unconventional because of this very low signal scenario. Microseismics will record for 24/7 into 365. We have used a node in Assam for microseismic for the velocity point only. Passive seismics also we have used, and the microseismics also with the node we tried. This is one technique which is going to be very good for unconventional, and be an unconventional geophysicist or geologist, because we have to go in the reservoir characterization to a finer scale. Reservoir heterogeneity identification is a must. Anisotropy, curvature, and microseismic monitoring of hydrocarbon simulations, hydraulic simulations are to be understood properly before going for an unconventional reservoir. Here is the workflow or outline for unconventional resources exploitation and development. It is not by me, it is I have taken from Vasilis et al. In 2011. You can see here seismic 2D, 3D, special processing, geological structures, petrophysics, microseismics, and then coming to the development stage, we are using the static reservoir modeling and dynamic reservoir modeling based on GCM, and then geocellular modeling, what we call, and then based on the seismic data. And then we are coming to the field development with the geomechanical effects and predict the performance of the reservoir in future. It's something like 4D scenario. So these are the developments in the geophysical and geological scenes, particularly based on seismics only. So here, it is the one which is to be clearly seen, because here the one which matters is the data quality, data amenability for a particular thing. Many a time we listen that seismic data we have used, but it has not given good results. Particularly, many of the people will say, but particularly before going for a particular advanced seismic techniques, we must be able to know that the data which we are using is conditioned enough to go for that particular one, or otherwise acquire the new data and go for the new technology. So make the case first and specify the technology. That is the catchword from my side. So seismic acquisition processing, we see that a lot of acquisition solutions we have. Dense spatial sampling we can see, microseismics as I have suggested we can go, P and SVO using the multi-component sensors we can take, and even hybrid exploration systems along with the nodes and normal cable systems have come, which has already been used by Oil India, and ONGC is also planning to do that. So such type of new innovative technologies in acquisition and advanced processing systems with multi or higher order NMO scenario. Still, I have seen that many of the people we use second order and fourth order velocity analysis, whereas the world is going for 32nd order or something. So such type of velocity analysis, even the anisotropic analysis have come into picture. So such type of things are to be implemented on the seismic to get into the finer scale reservoir characterization. In seismic interpretation, when we talk reservoir characterization, we have discussed all these things in this. And integrated interpolation is also more important. We can use non-seismic methods like microgravity surveys, airborne gravity surveys. Even the remote sensing gives a very good idea. Like VINGENS, I have seen in VINGENS, we have seen the remote sensing data, which is really very good. When I was GS in VINGEN, we have used the remote sensing data. And then seismic, well log, petrophysical and rock physics data inputs can be used. Then coming to the final, the ultimate is the seismic to simulation for unconventional reservoir development, where is the need is to close integration between the subsurface characterization and efficient engineering practices. So this comes under seismic guided drilling and logging while drilling and seismic while drilling. We can see the results at the wellbore. And then geophysics in describing the subsurface, rock type, fluid and fractures through seismic derived attributes, and the ability to convert the seismic amplitudes into desired rock properties. That depends upon the rocks and fluids under investigation, the particular model used for wave propagation and reflections from the earth, what model we have seen, and the model based advanced seismic data analysis, as I have already told, is a higher scale. Higher scale means earlier it was a basin scale reservoir characterization, then the reservoir scale reservoir characterization has come, and now we have to go one step ahead. There is a pore scale reservoir characterization which is being done now, and based on the quality of the seismic input data, the multi-azimuth data and full waveform inversion after that are giving a chance to look at the pore scale reservoir characterization. The pore pressure studies is the most important thing in case of unconventionals. We have used it in Andaman, we have used it in KG when we are looking at the Synrift scenarios, which plays a very crucial role in the risk reduction of seismic data. And then thank you for patient listening. I'm eager to listen from eminent scholar from NGRI. Thank you so much. Thank you, sir.
Thank you, sir. Thank you, Viseswara Garu. It's a very wonderful lecture.
Thank you.
As we know, your expertise in particular in ONGC on seismics,
Yes, sir.
and what we have expected, we received from you. Thank you very much. If any doubts are there, please, anybody want to clarify their doubts, they can clarify now on this topic.
I given the mail address also. If anybody has got anything, they can put on mail also. Later, even after studying the presentation, I'll share it to you, sir, for the students. Okay.
Yeah.
Any questions? Ready to answer.
So hoping that there are no questions from the participant side.
Yes, sir.
I know I request Hamadipti to introduce the next speaker of today's webinar, Dr. Nimisha Vedanti. Please, Hamadipti. Hello, Hamadipti is there? Hello. Yeah. Please go ahead.
Good morning, everyone. Myself, Hamadipti, allegedly studying second MSc Geophysics.
Hamadipti, 1 minute. Your voice is not audible. Your voice is not audible. Please increase your voice. Keep your mic near to your mouth.
Okay, sir.
Yeah, right.
Good morning, everyone. Myself, Hamadipti Alajingi, studying second MSc Geophysics. I am very glad to introduce Dr. Nimisha Vedanti Garu. Dr. Nimisha Vedanti received an MSc Tech in Exploration Geophysics from Banaras Hindu University and PhD from Osmania University, Hyderabad, while working at CSIR National Geophysical Research Institute. She held a postdoctoral position at the University of Texas at Austin, USA, and worked as CSIR Raman Research Fellow at the Department of Geoscience, University of Calgary, Canada. She was a visiting scientist in SINTEF Petroleum Research and Norwegian University of Science and Technology, Trondheim, Norway, under Indo-Norwegian collaboration programs, and had short research stay at the King Abdullah University of Science and Technology. Nimisha successfully led the Indo-Norwegian collaboration projects on seismic monitoring of in situ combustion process in Balol heavy oil field and feasibility assessment of a carbon dioxide enhanced oil recovery process in Ankleshwar oil field in collaboration with NTNU, SINTEF, and ONGC. Presently, she is in charge of shallow seismic group of CSIR, NGRI, and working on the exploration of shale gas and coal bed methane in Gondwana basins of India. Subbasalt imaging, 4D seismic monitoring, and assessment of carbon dioxide enhanced oil recovery are storage potential of key sedimentary basins of India. Nimisha is a recipient of many awards like the National Geoscience Award and CSIR Young Scientist Award. Society of Exploration Geophysicists USA has selected her as the honorary lecturer for South and East Asia in 2021. With this brief introduction, I now request Dr. Nimisha Vedanti Garu to deliver her lecture. Thank you.
Thank you. Thank you, Hamidipti. And morning, Rao sir. It's nice to see you and listen to your talk after a long time. We met last SPG in Kochi. That was the last conference I attended. After that, no official travel as such. So I hope you will enjoy my this talk, because now I switched over to a different field. This coal bed methane and shale gas. That's the my group is working on. Sir, I am sharing now my slide. Is it visible, the full screen?
Yes, madam. Please, go ahead. Please go ahead. It is visible.
Okay, yes. So, as Hemdipti already introduced me, so I don't have to say anything about that. But my mail ID is here in case someone wants to discuss something offline after my presentation. So basically, I'll share some of the results of what we had been working in our group on CBM and shale gas exploration, and why we are working on Gondwana basins of Eastern India. That also I'll explain quickly. And it was really nice to hear Professor Dr. Rao, because he has covered a lot many things in the introduction, and now you all must be having a fair idea of what are these unconventional reservoirs. So I try to keep the introduction short because he has covered most of the important things very nicely. I'll then straight away go to the Indian scenario for CBM development and shale gas exploration in the prospective basins. And then, since I'm from a practical group which are working in this for the CBM and shale gas exploration, I'll show you some of the geological complexities that we are facing to acquire seismic data in that area. And as Mr. Rao has already pointed out very nicely, that many people blame that seismic is not working, but then they do not really see that what was the data quality. So that's why I have put a question mark on this topic, that seismic prospecting for CBM and shale gas exploration, because what we have found that large amount of data which was acquired earlier was not of the adequate quality to meet the unconventional reservoir standard, as pointed out by Mr. Rao in his wonderful presentation. So I'll show you some of the real field examples that we have worked on, and I'll quickly discuss the road ahead, that how we can go ahead with the unconventional gas, the CBM and shale gas. So in the recent years, we all know, especially in this in the COVID and post-COVID era, there is a resurgence. In fact, it was before that also, that there was a resurgence in natural gas. And many people now are talking about that oil-free, and sometimes they are also talking about this fossil fuel-free energy sector and all. So it looks like that most of the people in the Western world would like to go for a wind and solar power. But many countries like India, there is it's really very far for us, all of us, to suddenly switch over to the wind and solar power and all these clean energy sources. So what are the low carbon alternative of the fossil fuel, the conventional fossil fuel? So as DGS has rightly categorized CBM and shale gas under the clean fuel, and with the advancement in the clean coal technologies and all, we really see that CBM and shale gas will adjust the energy structure for India's sustainable growth. Because one more point which I would like to cover very quickly is there is a CCS aspect also when we go for either CBM or shale gas exploration, especially when we are working in the coal fields. So it's really an interesting topic for a researcher to work on in future if you want to continue in the geophysics. So this is the figure. I'm sorry I did not put the right reference here, but you find this figure, this type of figures everywhere if you Google search, that everyone is talking about the expanding gap between demand and supply of the energy sources, either gas or fossil fuel or the total energy, whatever it is. But the gap between our demand and the supply, what we are getting in the domestic supply, is expanding every day because we are growing. Our economy is growing, and that's a good sign that our energy demand should increase. But the problem is, how do we meet that gap? So as you see that in 2016, in 2016-17, it was the gap was just 218 million metric cubic meter, but as with time it is increasing, and it is projected with some simulation models that it will touch a very high figure of 482 482 MMSCMD. So how do we meet that? There are several options that DGH has also recommended, that go for the enhanced oil recovery, and then also go for the unconventional exploration, and of course the basins like the basalt and all that Dr. Rao has covered, that's a basalt imaging issues and all. So all these new things, they have different technological challenges. And in today's talk, we cannot cover all of them because of the basalt imaging issues are different. We all know that we have large reserves, large Deccan basalt covered basins, and probably north of that Deccan basalt cover area might be very prospective in Mesozoic oil and gas. But there are again technological issues that why the exploration has not taken place at the pace in those areas. So we cannot cover all that today. Now coming to the enhanced oil recovery, improved oil recovery, DGS is putting a lot of pressure on the oil industry to go with this process, and also there is a pressure from the Atmanirbhar Bharat program also that enhance this production so that our import cost is reduced. But there are again lot of technology dependence and on the foreign countries, even in the EOR, IOR method, and not much domestic research is being pushed in that direction. So there are certain issues with the EOR, IOR techniques also. But I'll focus basically on the unconventional gas, the shale gas and CBM, which is produced like conventional gas, that will certainly bring down this gap to a very large extent, and we can probably survive for next 100 years without really going for an import or really going for any eco-friendly practice, as Mr. Rao has already pointed out in his presentation. So this type of figure, he has also shown, but in a different manner, that when we characterize the different type of reservoir, what do we mean by conventional, unconventional, what is tight oil, what is shale oil? He has explained it in terms of the physical properties and all. But here, since the students are from geology and geophysics, you already know what type of structures are these. So if I say the vertical scale is depth, you can clearly see that the coal bed methane, the one of the most talked unconventional hydrocarbon, is at very shallow depth, because all the coal mines, all the coal seams are at very shallow. They are sometimes above the groundwater table also. So there is not much depth issue. And if you see the rock properties of the coal, it should not be really a challenge to map the coal seams. It should not be really a challenge to extract the coal bed methane. But still it is called as unconventional because it's not the conventional natural gas what we find in the our conventional oil reservoir. But there are not too much of production issues associated with the CBM production. The left side, this is very clear and structural hydrocarbon pool, like an anticline you can see. So This type of structures are generally easy to be mapped using the seismic data. All you have to do is to acquire good data and then do a very good processing so that the structures are visible in the time migrated sections. So it's not very difficult to map this type of structures in the seismic data, that you all know. But when it comes to unconventional reservoirs, what Dr. Rao has already mentioned, the source rock reservoirs, now I would say that the shale oil or the shale gas, here you see that they are at much deeper level. And you all know that when we acquire seismic, the deeper you go, the resolution of the seismic becomes very poor. And most of the time, these beds are not as thick as the conventional sandstone reservoirs would be. So detecting those type of reservoirs, even if it is a horizontal stratification that we are mapping, still it becomes difficult to map that. And again, with the temperature and pressure which changes with the depth, the properties of these reservoirs at depth, it becomes difficult sometimes to distinguish the source rock from, sometimes even difficult with distinguish it with respect to basement also. You don't find that much impedance contrast in the seismic section to pinpoint that, okay, this is my basement and this is the shale layer above it. Sometimes it becomes very, very difficult, especially if our data quality is not good. So these are the challenges that seismic, the geophysicist would face while working for the exploration of coal bed methane and the shale gas exploration. With coal bed methane, ideally there should not be a problem because we know it's a highly porous rock, low velocity, low density. It's not difficult to identify a coal bed in a sand shale lithology. But what happens is most of the coal fields, when I show you real data, it's not the problem of the source rock mapping issue. It's more of a geological and stratigraphic problem that what we are facing while mapping the coal bed methane reservoirs. So this is the same triangle what Mr. Rao has presented, but we have modified it to explain it that we are looking for, what I am talking is the source rock unconventional oil. I'm not, if I plot it the way he has done with respect to the permeability, then coal bed methane will not come at the same point where shale gas is mentioned, because we all know that the permeability of the shale rock can be very different from the coal beds. And definitely coal beds are very, at least the upper ones have good permeability and high porosity. But here they are placed in the same place in the triangle because there are some similar issues while exploring coal bed methane and shale gas from the reservoir, because they both are in source rock. In the both case, the gas in the formation can be either in the absorbed state or in the sometimes in the coal bed there is an outburst also. So it's very different from the conventional reservoir where you have a separate oil pool above the water pool. So detecting that type of fuel, the oil or gas, whatever it is in the source rock from the seismic signatures, it becomes really very difficult if you compare it with the conventional reservoir exploration. So conventional reservoir, you already know that after Dr. Rao's talk that it's easy, that the straightforward procedures are there for their extractions. But here you see the picture is shown the right side when this is a shale, that how compact it is, and you can imagine that if something has to move inside this rock formation, a fluid, how difficult it is to make it move inside to move it towards the production well. So these are the production challenges that people face in the unconventional. And when we call the unconventional, we also talk about the tight gas also, because it's not, though it is a sandstone reservoir, but what happens is the porosity and the permeability of the tight sand is not good. And sometimes even the good sandstone reservoir, which might look that it has a very nice porosity, but if the void spaces are isolated, then also it cannot be a good reservoir rock, and it cannot produce hydrocarbon in ideal situation. distribution. The ideal reservoir, which is conventional and easy to produce, should look like this right one. That the void spaces present in the rock should be interconnected, and that's how it can be. It doesn't offer any friction for the production. How do coal beds look? This is a real picture I have taken from the wiki, one website, the reference is given. So when we go to the coal field, most of the time in coal fields, you see the coal seams are, you can see directly. This is like from an open cast, this coal mine. And you see all the coal beds are this stratification of the coal bed, and there is some parting, some sediments are deposited between different coal layers. Now, when we acquire the seismic data, it depends upon the resolution of the seismic data that whether we are able to resolve all these coal seams separately, or we see them as a pack and then we call it as a pack of coal seams, or we just try to map the top of the topmost coal seam and then say, okay, the coal seam starts from here, and then afterward we do have a resolution problem that we are not able to extract the, we are not able to delineate these thin coal seams. But if our data resolution is really good, I will show you some of the results. It is possible to delineate even 2 meter thin coal seams also, and that we have done it. So you already know that what is coal bed methane. Rao has already talked about that, so I'll not read this again. But the thing is, when we go for coal field exploration, there are two important factors we should keep in mind. That the topmost coal, that is mineable. So generally the coal mining companies would like to mine that coal and make use of that. So when we go for the CBM, what we look for the little deeper coal seams which may not be mineable, and these seams can also serve as a reservoir, as a storage reservoir for carbon dioxide sequestration also. And we have a very good chance in India to go ahead with this type of problems because we are already identified as a major CBM player globally. And the only countries above us are US, Canada, Australia, and China. And we do really have a good future in CBM exploration. So I'm coming back to that slide again because the coal field exploration issues where we are mapping the coal seams are interesting because in the same coal field, we do have the shale also. And the coal field shale formations are also found very prospective and commercially viable for the shale gas exploration. So if we work in a coal field using seismic exploration, we solve three problems at a stretch, that we are able to map the coal seams, extract the coal, we are able to identify the CBM reservoirs, extract the CBM gas. We are in the same place if our data is good and the acquisition and processing has been done beautifully. We can map the deeper shale layers, and we can also think about the shale gas exploration. And in addition to that, there is an added advantage of the CCS option in the unminable coal seams and also in the shale gas rocks, where after production of the shale, after exploration of gas, CO2 can be injected in that. So this type of situation, if you remember, that top coal and then below deeper shales, we find in most of the Gondwana coal fields. And this is one generalized stratigraphic section I am showing from a Raniganj subbasin, which is one of the most prospective area of the Damodar Valley field, but Dr. Rao has already mentioned. So if just by conducting one set of 3D survey, we'll be able to map the coal seams, we'll be able to map the shale gas formations, and also after production, we can look into these formations again for the CCS option. So in most of the areas in those Damodar Valley coal fields, we expect shales at very depth, below 1.5 to 2 kilometer depth. So our experiment should be designed very carefully to map, to have good resolution at that depth. So these are the Gondwana fields which mark in an oval here. And you see the left side figure, these are the coal fields of India, all these black these black dots. You see all the coal fields are situated in this part of the India. Of course, there are some here, but the most prospective ones are here in the eastern part of the India. And out of that, this Damodar Valley basin, which is blue circle here, is the most prospective both for high quality coal and thus for CPM and also for the shale gas. So the only program which Coal India has launched for the shale gas exploration lies in this basin. So I'll confine to this basin today. So I take here this one opportunity to quickly tell you that why we, means we are in for the coal exploration as well. Because if you see this figure here, that still India's major energy need is being supported by the coal. So there is a lot of talk in foreign media that India should not go ahead with the coal exploration programs as was promised by the Prime Minister. But the problem is we cannot suddenly stop this, because there are more than 7 lakh people involved in the employment. And of course, the number is much higher. When I prepared this slide, it was this, but I'm sure the number is high. And we do have 5th largest coal reserves in the world. So what we have, if we are not using that, then it's not really a good economic situation for India if we just ignore the largest coal reserves we have. What we have to do is we should look for the clean coal technology options and also go for the CCS options, because there are a lot of issues associated with the coal mining and the production of gas in the coal fields, which are not eco-friendly. But there are solutions for that which can be looked into, and Coal India is seriously looking into that option. So that's why a lot of old data sets are being revised, being relooked into, and then they are trying to see that how some of the coal basins, especially in the Damodar Valley, can be explored for CBM and shale gas, and also for the CCS aspects. So the initial work was done by the Geological Survey of India, where they have mentioned that the Gondwana coal fields have the highest rank of coal, and that's why the thermogenic methane reservoirs are also expected there. But the old data set what GSI had, there is no seismic exploration done those days. So whatever data this was given, this was a report submitted to the Lok Sabha in 2016 for the CPM, and they have been presented that total CPM resources probably we have this 91.8 TCF, but this estimate was not given by using the seismic exploration or the detailed exploration. It was from a very sparse data set collected by GSI and long back, basically for the coal exploration, not for the CBM or shale gas. So this figure might change. But even with this, you can see that though we know that approximately this much is available, the established is just the 10% of that, almost 10% of that. So which means lot many efforts which were put by the Coal India and other companies to explore CBM in several blocks failed. That failed because there was not much geophysical study done in that area, and although Ministry of Petroleum and Natural Gas has carved out 26,000 square kilometer area in Gondwana Basin for CBM exploration, very little part of that area has been explored using the seismic data. And mostly they are dependent upon the wells which are very sparsely located. And then you all know that when there is no continuous information, there will be a problem in estimating the resources. Similar the case with the shale gas also. So this slide shows that the most optimistic shale gas potential was given by the Schlumberger, that is 2100 TCF. I do not know how did they estimate this, but this was for the entire country. But the least one, which USGS has given, that is 6.1 TCF, and that too they did not cover all the basins, only Cambay, KG and Kaveri they have covered. So it's still high. So which means that India has really very good shale gas potential, and there is a need to relook into all these fields. The CMPDI, Coal India's research wing, they have estimated 45 TCF of shale gas in the in some of their coal fields. That includes Damodar Valley Basin, where the potential is very high. This is the figure what Dr. Rao has already shown, and he has also shown that the Gondwana Basin, the Damodar River Valley Basin, which is a prospective basin for shale gas exploration, which is lying in the prospective coal field. So this is one table we have taken from EIA study. So here you see the Damodar Valley Basin, which is the coalfield, Damodar Valley coalfield area, is they have put it that recoverable TCF 7, which is a very good value, though it is not, we really honestly, we do not know what should be the value here, but still it is tentative value also is very promising that we should go for the exploration programs in the Damodar Valley Basin. And we have also found from our studies that we carried out in GRA that there is the shale gas present in this coal field is commercially viable to be produced. Now, so NGRI and CMPTI and another lab of CSIR SIMFER will launch coal bed methane and shale gas exploration programs in this Gondwana basins using seismic exploration studies, and then the laboratory studies being carried out by CMPTI and SIMFER in parallel. So our part was basically to see if we are able to map the formations, the structures, and we can give the clear image of the subsurface formations in this basin. The problem what we face with the seismic exploration is, I'll show you that why the good quality of data and good quality of processing is really required when we go for this type of unconventional exploration. So this is a geological map you see we have taken from a book published by Datta in 2003. So there are different formations. I will show you the stratigraphy in the next slide. Here there are producing blocks, CBM producing blocks in this field, and you see that this basin is highly faulted. All these red lines are the faults here. And in addition to that, this is the green one is the Talcher formation, which is the base of the Gondwana stratigraphy. So you see the Talcher formation is already exposed as an outcrop, which means the basin has been tectonically very active. Many things have happened that the bottommost formation is also at the surface. So it's not going to be easy to map the to map all the stratigraphic features in these basins just by using the seismic data. The Raniganj formation should be the topmost Gondwana formation in this area. You see this light gray color, it is here, and most of the CBM producing blocks are in this Raniganj formation. And we are also looking for the deeper shale in this formation, only in the Raniganj formation. And the Barakar formation, the dark gray, you see, this is known for a good quality coal. So for all the CBM exploration projects, the Barakar, and for, of course, for the coal also, deeper coals also, this formation mapping is important, the Barakar. So when we go for exploration in the coal fields, we look for the Raniganj formation, we look for the Barakar formation, and the most important formation, Baran measure, which is very prospective, which is actually the most prospective for the shale gas, is missing in this map. So it is at depth because this is a surface geological map. So if you see the vertical stratigraphy, you see that this is the standard stratigraphy in most of the Gondwana coal fields, that we have the topmost formation Raniganj. Then we have Baran measure. So Raniganj formation is basically a sandstone shale coal seam alternating sequence formation. So detecting this type of Raniganj formation top and the faults within Raniganj formation was not really that difficult, and because it's at 1000-meter depth, and generally we have okay data in that area, and there is a good contrast between the coal seam, sandstone and shale. But then comes the Baran measure, where there are no coal seams. The Baran measure is completely devoid of any coal seams. It's only the shale, and this is the main formation any oil industry will look for a shale gas exploration. So most of the time we do not find any contrast between the base of the Raniganj formation and the top of the Baran measure. Similarly for the Barakar also, if the Barakar formation we are, because we do not find the coal seam at the top of the Barakar formation, we sometimes We cannot mark in the seismic that where is the top of the Barakkar formation. We can mark the top of the coal seam, which is shown here in the black, but we are not able to map the top of the Barakkar formations unless a well-log data is given. And most of the time when you are going to the virgin area, the exploratory wells are drilled after you present the seismic interpretation to them. So at this stage of exploration, we are just on our own, just on the basis of, with the seismic, blindly playing with these formations that where to put them. The base of the Gondwana formation is the Talcher formation. Sometimes because of its depth, its compactness, we are able to detect the Talcher formation. But many times again, this formation, the top is not able, we are not able to detect. And many times there is not much contrast between the metamorphic basement underlying the Talcher. So these are the issues we face when we go to a coalfield exploration. And you see, as you see that all this is within 1 to 1.5 kilometer of the top coast. So when we go for the conventional exploration, most of the time our reservoirs start beyond 1 kilometer. So we are out of, means we won't be in the near surface issues. But here when we go for the coalfield exploration, we have to deal with lot many near surface noises issue, and we cannot just ignore that. And we also have these geological complexities, which I have made it based upon my practical experience. I might be wrong in some case, but this is based on my practical experience while working on this type of data. That in most of these basins, we do have this lot of these dikes, faults, and the coal layers. They are very porous, and sometimes they start right from the top. So they are so attenuating that whatever seismic energy we are impounding on the surface, it doesn't reach to our target depth. So that was, and the dikes, they are another problem. So what we get is a low signal to noise ratio. Then we have many lateral discontinuities, and most of the seismic processing methods are not sensitive to the standard ones, are not really sensitive to the lateral discontinuity mapping. Then we have to work on some high advanced method to account for this. Then the coal layers and the dikes, they are also responsible for the short period multiples. And on top of all these things, we do have elevation issues in most of the areas that we have surveyed. That elevation changes so much that the static correction becomes really cumbersome for us. So all this result in a poor quality seismic image. So that what I want to say here, we cannot really go without a proper planning, without a proper survey design to a coalfield. It's going to generate a very poor quality seismic image, and in the end we'll say that seismic is not useful. Other than that geological issues, we do have some lithological complexities. As I mentioned earlier, that this basin experienced multi-period tectonic activities. So that has affected the stratification. So what we expect that the deeper beds will have the higher velocity and the lower will not have. So those type of things are not really seen in this type of basin. We also seen overriding of older strata over the younger one. We also saw that in the image what I showed, the Raniganj basin, that the Talcher, the bottom was at the top of the, like an outcrop it was there. There are a lot of termination of seams and shale pottings which are beyond the resolution of the seismic data. And as I mentioned that the impedance contrast many times is not sufficient to detect the boundaries. But having said all that, can we say that CBM exploration, means can the seismic will be useful for CBM exploration? Then yes, the answer is theoretically yes. But then we have to go for good quality data acquisition, and we have to be very careful while doing structural interpretation. In addition to that, we need to really try to obtain the good impedance and the Poisson's ratio. So that's why now we are going to acquire at least 2D 3-component data so that we control the Poisson's ratio in that region. We tried to do this frequency spectrum decomposition, but the problem is the signal to noise ratio is so high that any frequency based analysis is not really helping us at this moment. And the amplitudes also are so compromised that at this moment it is difficult to include any type of AVO procedure to detect the lithology in this data. But theoretically, yes. And the same is the case with the shale gas, because in the same area we are going to look for the shale gas results. So unless the overlying strata is properly mapped, we cannot really put shale at certain depth. And we do, and then in the absence of this contrast with the shale and other rocks, it becomes very challenging. And for shale, like Dr. Rao has already mentioned, that it's not just the production, even the seismic signature over shale, there is so much anisotropy in that, and any signature will depend upon the TOC content, the minerals present in the shale, that we cannot really easily distinguish between shale and soil unless we have the knowledge of the mineralogy and TOC content. So the geophysical logs are really required when we go for this type of studies. But hence, only by using seismic data at the exploration stage in virgin area, it becomes really problem to delineate this thing. So and the take home from all those slides is the conventional seismic prospecting is not sufficient when we go for the cold field exploration. You need to have a high resolution data, and we should also have the logs with us so that we control the velocities and we control sometimes depth in certain areas. So to address these things, we are doing some research projects with the existing data sets in the same Damodar Valley coal field. And again, I'm repeating this slide that here you see that we are working on mapping these coal seams, all the thin coal seams in this formation and the shale formations, given we have a very complex overburden in the Raniganj. So we initially we were acquiring data using the explosives, but now the permission is not available. So we have two types of vibroseismic sources. This is the bigger one, which generates the compressional wave with this movement. The plate movement is vertical up and down, so only compressional waves are generated. And the frequency range for this vibrator is from 10 to 250 hertz. We have another smaller vibrator which does not produce that much energy, but that can be used as a SWF source also. And the frequency range is from 10 to 450 hertz. So we are using these two vibrators as a seismic source. Now, having said that, when we started using the vibrator source, we started seeing problem in the wavelets what we are being generated. Because when we know that the dynamite, when we use the explosive, the spike signature is generated, but the vibrator, it generates a sweep type of signal, and because of some inherent issues in the vibrator control system, we do not really get a proper sweep. You see the bottom picture, this is the recorded sweep what we get. Ideally we expect the upper one. So this also produces noise. You see the noise spectrum here. This produces noise, additional noise, just because we change the source now. Now, what happens with these type of issues is we of course expect a lot of ground roll in the airwaves when we acquire the land seismic data. But ideally, the right side panel, the rightmost panel, you see that ideally it should not cover the entire seismic entire short gather. But what we see in our data is the ground roll mostly covers all the offsets, and the entire short gather is heavily covered with the ground roll. So this issue is coming mainly because of use of the vibroseis, and we are really in a problem to get rid of these and then detect these reflections which are not really visible at all in this section. And this is one of the cleaner sections we have was data. So the standard processing sequence, what we had been taught till now, most of the time it doesn't work when we are not able to get rid of these noises using the conventional FK filters and all. So many times we had nothing but to apply the surgical mute, and lot of data was lost with that. But now we had been working on certain new type of filters which we call as the morphological filters, which are like the structural attributes we see in the data, and then we try to get rid of those attributes by modeling their structures. But still, even with those type of applications, you see, we are not able to really improve the reflections in the data. But of course, the stack section has improved. Now we are trying to use this ground roll modeling algorithms to get rid of these noises. So that is still a research stage. We are doing that. So right now I do not have any section to show that. So having done all that, we have processed some of the data set. This is from the Raniganj basin, and you see that we could not really help to improve the near data, the near surface data. It doesn't give any information, but in the deeper formations, we are able to map the reflectors properly, and the faults are mapped in the faults in the coal seams are mapped with this type of processing. But now we are focusing to improve the near surface also, because some of the formations the company is interested are in near surface, and that we could not map it properly. And in another basin, in the Damodar Valley basin only, but in another block, we encountered a shallow dipping basement, and this was being explored for the shale gas exploration. But you see that at this point the basement is almost at the surface, so this was not really a suitable area for the shale gas exploration program. So we recommended that we should move towards this is a north-south I think line. So we should move to little south to go into the deeper part of the basin, so that we can map the shale formations, and we prepared the depth contour map of the shallow basement. That we discarded this area for the exploration. We also estimated the contour map of the barren measure formation. This is a very rough calculation because the control points were less, but approximately you see the thickness of the barren measure is around 300 meter everywhere in Raniganj basin, and the barren measure is the most prospective one for the shale gas exploration. And studies carried out by Semper further after we submitted our report has shown that it is really prospective for that. So now we are working on the improving on the velocities, because with this type of data, we are not really able to generate a smooth velocity section, and the stack section or the time migrated section doesn't look that appealing as it should look like for the conventional oil exploration thing. So we are now using these geostatistical methods, also using the log information from the logs to improve our velocities and our interpretation, and which has really improved our resolution also. So here, unfortunately, I'm not able to show the area and location because the reports are still under submission and the work is under review. But you can see that all these thin seams, this 1, 2, 3, 4, these all were the thin seams which were resolved with the high resolution processing, and the 7 and 8 were the regional seams in that area which were also mapped in this. Then in fact we improved this one with the geostatistical information, and we carried out the stochastic inversion also, and we further improved, and we reported the shale partings also. So with this 1 and 2 meter coal seams also we could report with this type of inversion method. So having done that, we generally generate the roof and floor contour map for a coal seam, which is nothing but top and bottom of the reservoir, I would say, if we compare with the conventional hydrocarbon ones. So in coal seams, we call it roof map and the floor contour map. So with that, the drilling engineers take a decision that how to go ahead with the drilling. So we see that there are so many wells given at later stage to us, and we see that the errors in the depth estimates given by us after geostatistical inversion is acceptable. In some cases, it's very good. So these are the different seam tops and floor I'm showing that how did we work on to reducing the error in the depth estimates coming from seismic and from the wells. Now, another thing what we are trying to see that if we are able to distinguish a non-burst coal seam from a outburst coal seam, and we are trying to see if impedance can provide an information. So studies have shown that the ultrasonic velocity of non-outburst coal seam is approximately 1.5 times that of a gas outburst coal seam. But this study we have not done at NGRA. We have to do that because now we received codes also. So now we have to do this type of study further to understand this type of procedures. We will see that the impedance is changing in the roof of the seam, and impedance is changing in the floor of the seam. And this is the upper regional seam, and in the lower, this image is much clear that you see a lower impedance in the roof and the floor of that seam is completely higher impedance, which is possible that maybe this is an outburst case. But if I compare with the upper seam, I'm not able to interpret this. So we really need to understand that how impedance relates to the outbursts. And then our collaborators, they carried CMPDI, they carried out drilling, and SIMFER has analyzed the different data sets in their lab. And we came up with this result that this is of course for a very small area, but in general what we have what we have recommended is the Raniganj Basin is really prospective for both CBM and shale gas. And similarly, the entire Damodar Valley Basin should be explored the way we have done for the Raniganj one. But having said that, we really need to work on innovative technologies when it comes to seismic, and the well, some information from the well and with the laboratory investigations is really important if we are going to give a realistic estimate for that basin. I'll show this is not from the our work here. This I worked when I was in Raman Research Fellow. I was working for the Western Canada Sedimentary Basin. So I just want to show that the data quality was so good that we were able to map all the faults in the seismic. These are the major faults, as you see in dark blue lines here. And these are the curvature anomalies which came, and these are the incoherency also. These anomalies came very nicely when the data was processed properly. And this is from this is the curvature anomaly, and this is from, I think, top of the carbonate one, where we were looking into the fracture connectivity and how fracture propagation is happening in that shale gas reservoir. So coming back to Indian situation, what I suggest that road ahead is we should really start doing the seismic exploration in these Damodar Valley and other sub-basin, and preferably we should acquire some lines at least 3C, so that we have good control on the presence ratio. And the survey designing is really important. One thing I could not show here is there are lot many inaccessible patches and villages when we are given an area in the coal fields, because it's all habitated. So we will have always low fold in the, mostly in the high target area, the foldage will be low. So we are working on technologies which can cover the fold issue. And in that case, the survey designing is really important, so that we cancel the noise and we overcome the problem which the low foldage causes. We are also required to work on the techniques to update the velocity models, because when we convert to depth, it's the velocity that plays the role. And right now, we do not really have very good control on the velocities. Then one of the most important thing is rock physics modeling for coal and shale is important. We do not really have a proper rock physics model for both, because both the rocks are anisotropic, and we really need to understand that what role anisotropy is playing, and we should do the anisotropic rock physics modeling, not the standard one what we had been doing for the conventional reservoir. And after that, the integrated reservoir characterization and the core analysis and quantitative evaluation will be required to give the resource potential of that area. And on top of that, especially in the coal field, we are recommending the acquisition of either deep resistivity or some electromagnetic methods, because if we are able to map all the coal seams properly, they are very resistive. So you cannot mess it with the resistivity or conductivity data. And they are not that sensitive to some of the noises that seismic is facing. So if we do it combinedly, then we can really constrain our near surface image, and that will help us to improve our deeper image also. So thank you.
Thank you, Dr. Nimisha Vadanti, for presenting a very nice way about the coal bed methane and shale gas reserves in India, and research being carried out by NGRI in these fields. So I request participants to have, if you have any doubts, please clarify. Sir Sivirao, sir,
Yeah.
you want to have something in your mind, I think.
Dr. Nimisha, it's an excellent work done. That's what
Thank you,
first
sir.
comment.
Thank you, sir.
Because incidentally, I was born and brought up in Jharia, so I'm interested in coal. So firstly, I have seen that the seismic, as you said, it is having a lot of problems in the near surface.
Yes, sir.
The same problem we have faced in Rajasthan also. Near surface has got a lot of problems. Particularly, what we have done is for the velocity model, we did a near surface velocity model separately and incorporated in the main velocity model to take care of the near surface low frequency events. One way. The other way is to go ahead with the data with 5D interpolation, which will fill the gaps and remove the noises in many of the things. That is one of the suggestions. That's all. But otherwise, with that particular data, the where amenability is one of the biggest issues. You could do that particular roof and bottom one also. It's an excellent job done. I'm really fascinated to see that. Thank you and congratulations for that doing that job.
Thank you, sir. Thank you.
Okay, thank you. That's what I want to share.
Thank you, Dr. Nimisha Vedanti, once again. Thank you very much. Now, can I move to the next lecture? If there are no questions, I think. So now I request Mrs. Sirisha Bhargavi to introduce our next speaker, Dr. N. Satyavani. Shirisha Bhargavi. Shirisha Bhargavi, are you there? So, Webmaster Srinivas Ragar. Hello. Yeah, please you switch on your Sirisha Bhargavi. Webmaster.
A very good morning to one and all. I'm very glad to present myself, Sai Bhargavi Sirisha Vaspalli, currently pursuing MSc Geophysics final year. Now, I would like to take the privilege of introducing our today's speaker, Dr. N. Satyavani Garu. Dr. N. Satyavani, currently working as principal scientist in the seismic group of CSIR NGRA, has completed MSc Tech in Exploration Geophysics from Andhra University in 1998, and thereafter joined NGRA as a project fellow in the CSS group of NGRA. She was awarded PhD in 2002 for the novel approach developed by her to delineate the seismic velocities from the CDP reflection data in presence of dipping strata in the Aravalli Fold Belt region. Thereafter, she joined Gas Heighted Group and is actively engaged in the niche areas of seismic data processing, seismic attribute analysis, travel time tomography, pre-stack depth migration, and seismic interpretation. She has participated in the field crews for the seismic data acquisition for gas hydrates carried out by the NGRA in the eastern margin of India. She is member of Geological Society of India, European Association of Geoscientists and Engineers, and Society of Exploration Geophysics. She is the recipient of K.R. Gupta Gold Medal, conferred by Geological Society of India, and National Geoscience Award by the Ministry of Science. She has authored about 29 research papers in various geophysical journals. I now request Dr. N. Satyavani Garu to deliver her lecture. I thank each and everyone for giving me this wonderful opportunity. Thank you.
Hello. Sir, is there any problem? I am Satyavani, ma'am. Is there any problem?
Yeah. Unmuting
Satyavani.
problem is there.
Madam, please unmute your.
Just wait. Webmaster, please unmute Satyavani madam.
Yes.
Yeah, am I audible?
Yeah.
Yeah. Good morning to everybody who is over here, all the students, C.V. Rao sir, Nimisha, Swami sir. At the outset, I would like to thank the university, Nannaya University, for giving me this opportunity to make a small presentation for the benefit of the students. And my presentation would be mostly concentrated on gas hydrates because we are dealing with unconventional resources. And thanks to C.V. Rao sir, most of the introductory part I can now skip because most of the introduction has been dealt by him. So I will just try to present whatever with some background, whatever has been done in NGRI and what is the world status and things like that. Now coming to my presentation, I would just start to share my screen. Yeah, is this visible?
Yes, visible.
Yes.
Yes. So, my presentation would be mostly concentrated on the seismic methods and exploration of gas hydrates. Because I have been working on seismic methods right from my entry into NGRI till date. This has been one of my favorite fields, and also fortunately, I have been working in the same line. For this presentation, I will exclusively deal with the using seismic method, and then how do we use them in exploration of gas hydrates. Now, why only gas hydrates? That is something that I will be dealing with in the next slides. The presentation outlay, we would mostly concentrate on the significance of gas hydrate, how they are formed, and where we can find them. So these three will be the general introduction of the gas hydrate. And then we will come to the identification aspects, how seismic methods will help in identification. Then I'll deal with some examples of BSR from India. And then we will move into some studies done by NGRI in terms of identification. And then we will move to geologic proxies, how geology will come into picture when we can in the identification of gas hydrate. And finally, we will go to the resource estimates. And here also I will, this will be based on some examples from NGRI. Now coming to the significance part, why we should look at gas hydrates at all? The main concern here is the amount of gas that is coming out. If you see, if you can somehow dissociate 1 meter cube of gas hydrate under standard temperature and pressure conditions, what you get would be 164 meter cube of free gas and 0.8 meter cube of water. Now it is this 164 meter cube of free gas which is very attractive, which makes gas hydrates one of the most abundant resource, I should say. And this is also the reason why world countries are all focused on exploring gas hydrate. Now coming to the situation worldwide as to how much of gas hydrate or gas is present in the hydrate bearing sand. So if you come, if we see, we have the pie diagram of all the countries, and India is somewhere over here, which says 933 trillion cubic feet of free gas is available in the gas hydrates of the continental margin. This is a conservative estimate and just an estimate. And many studies are being focused to either ratify or increase this estimate as much as possible. Now coming to the resource triangle, this triangle, I think both the earlier presenters have shown this triangle. What I want to emphasize here is the base of this pyramid. If you can see, gas hydrates is the base of this pyramid, which says this is the one, this is the resource, unconventional resource, which has highest potential or highest abundance of free gas. Now coming to the next slide, what are gas hydrates and how they are formed? Like gas hydrates are nothing but ice-like compounds. They look just like ice. I will show you some more figures, which occur in nature as crystalline solids in the form of ice, where gas molecules are trapped by the lattice of water molecules, forming cage-like structures. If you see here, now the blue one is the gas molecule, and then you have this water crystal lattice, H2O, these two O, and this is the H. Instead of H, you will have the methane for not instead of H. In the cages of water molecules, we have the gas molecule which is locked inside the cage. Now there are various arrangements you can call, and based on those arrangements, there are forms of hydrates. Like if you go by the molecular numbers, if we have the structure 1 hydrate, then we have methane, ethane, and carbon dioxide, which form the central part of the cage. And for structure 2, we have the higher hydrocarbons like propane, isobutane, natural gas, etc. And even further, which is structure 2. And then we have other higher compounds which are not of our of concern for the present study. What we will be concerned is mostly methane, because this is the most abundant methane. In some cases, propane is also done, but it is very rare. Now, coming to how we get the methane, from where we are getting methane so that it enters into the water molecule. So whatever methane we are getting is mostly from the decomposition of the organic matter, because these are mostly found in the permafrost, in the continental margin regions. Sometimes this gas can also be thermogenic gas, which comes from deeply buried petroleum system, and this gas will travel through the faults. To show it pictorially, this is the continent and this is the water, the marine environment. So whatever is the biogenic material which is coming from the continent will get deposited on the seafloor, and because of this deposition subsurface, because of this decomposition of the organic matter, we get methane coming out, and then that methane, when mixes with this water which is already present in the sediment, it will form a cage-like structure. Now coming to the thermogenic methane, which is at a deeper place, from there there is a degeneration and there is a release of methane, and that methane will pass through these faults and it will get deposited within the sediments which are present here. And that methane again will get trapped into the water which is present inside in the sediment lattice. So this is how the gas hydrates are formed. More than gas hydrates, many of the times it is the free gas which is also present beneath the gas hydrates that is even more attractive. Once the gas hydrates are formed, they are, as I told earlier, they are ice-like solid substances. So they kind of cement the entire sediment layer. So the sediment layer with hydrate will now start acting as a seal. So whatever free gas is coming from beneath, whatever has been absorbed in the sand, in the sediment, will become a hydrate, which could not be absorbed, will start pulling up beneath the hydrate layer. So this is the free gas which is lying beneath the hydrate layer. So when we do a gas hydrate exploration, we are looking at both the hydrate within the free gas within the hydrate and also the free gas. But as of now, mostly worldwide, it is the free gas which is being targeted, because production of free gas from gas hydrate has not yet been proven. People are still trying to do some production tests which are till date not very satisfactory, except for one in Japan. Those studies for extracting free gas from the hydrate are still taking place. Now, coming to the conditions, what are the conditions at which these gas hydrates are formed? So they require very high pressure, low temperature, and high gas concentration. High pressure, the pressure will come from the overburdened water, because there is a complete seawater column below above the sediment. That will give the pressure. And then temperature, as you all know, as we go deep into the sea, the temperatures are very low. And only at those low temperatures, this ice kind of structures can be formed. And of course, we also need gas. Unless there is gas concentration, there will not be any methane that would enter into the stability and then form the hydrate. Now, what will happen if any of these conditions are not met? Either there is no hydrate formation, and if hydrate is once formed and then there is a change, some kind of change due to whatever reasons in the pressure and temperature, then there will be a full dissociation. The gas which was in the methane hydrate will disappear. It will dissociate. It will come out from the hydrate structures, hydrate crystal lattice. Where are they found? They are mostly found in nature, mostly in the permafrost region. If we are talking of polar regions like Alaska and some parts of Russia. And for other continental regions, it is found in the marine sediments, in the water depths, generally not exceeding 450-500 meters. This is what they say. But for India, it has been observed in KG Basin. Generally, water column depth was about 1,000 to 1,500 meter, which is like 1 to 1.5 kilometers below the. That was the water column which was required for the formation of hydrate in the KG Basin region. Okay, now coming to the worldwide occurrences. Now, as I told earlier, these are very lucrative, and worldwide there is extensive research going on gas hydrates. What are the regions where one can expect to see gas hydrates? Are the subduction zones like Nankai Trough, somewhere over here. Then we have Cascadia Basin here, and then we have Andaman region, somewhere over here. The specific subduction zones. Also, we find sometime in passive margins like Break Ridge, which is over here, and sometimes and also in the KG Basin, which is also a passive margin. And then we have offshore hydrocarbons like Gulf of Mexico, which is here, and then somewhere in Alaska, these regions. Okay. Coming to the Arctic permafrost, Mackenzie Arctic Alaska, which is again over here. This is Arctic Alaska, and this is offshore. And then we have some portions in Russia, somewhere over here. These, as you can see, these are all ice-covered regions. So here and here. So here we get the hydrates in permafrost. The yellow circles are showing the recovered gas hydrate, recovered by means of drilling and sea expeditions. And the red circles are showing inferred gas hydrate. From where is this inference made? The inference comes from the seismic studies. Now, what are the, as I told you earlier, there are three types of deposits. One is in the Arctic region, continental margin, and deep ocean. So this is your frozen surface ground, and this is Arctic deposit. That means this entire region is covered by ice. So these are your hydrate lenses. Excuse me. Which are, then we have a rig and then normal exploration things. And then this is the ocean. When we are talking of ocean, we are talking of the continental deposits. So as I told you, this is thermogenic methane which is coming from below in both the cases. And from the continent, if there is a organic matter deposition, and then over a period, this organic matter decomposes, and then we get then the hydrates are found because they take methane from the decomposition part. Coming to the mode of occurrence, as I told you, how are the hydrates formed and how do they leak? Now, this is a gas hydrate. As I told you, this looks like ice, very much ice-like thing, and it is within the sediment. Okay. Now, if there is a fracture within the sediment, these are all cores from one of the drilling expedition in KG Basin. So if there are fractures, the hydrates will fill those fractures, and this is how you get to see them as these white bands. These are all fracture fills. Or these are called massive hydrates, which is a total emplacement with wherever they find a void in the sediment structure, they go and simply occupy those voids. So you get this kind of filling thing, which is massive, which is called massive hydrate. And then if you see here, there are some small specks of hydrates here and there, that white patches kind of thing. These are disseminated hydrates which are forming in sands like this. Now this section, this is a sectional view of this core. So you can see how hydrates are forming. These are all the fractures which are present within the sediment matrix, and so you can see the hydrates occupying these fractures. So this is how the hydrates look, this is how they form, and this is how they occur. Now coming to the stability zones, as I told you earlier, gas hydrates will require a specific pressure and temperature so that the hydrates can be formed. So NGRA has made an attempt to find out what is the stability conditions or the stability zone. The stability zone is the place wherein the depth to which the gas hydrates are stable. That means which do not dissociate, which are still like hydrates. Now this is the gas hydrate phase boundary curve, which they call. So under, if you see this, this is the temperature and this is the depth. As I told you, the hydrates are very stable at low temperature. You can see them. The temperatures are going from below zero. And pressure is also very high. Pressure, we are talking in terms of depth, okay? Sea column depth. So somewhere over about 1,000, around 1,000 and deeper. And this is the phase boundary curve, which is called, this is the gas hydrate phase boundary curve, which will define the pressure and the temperature in terms of depth and temperature, wherein the hydrates would be stable. So this is the region where you can get hydrates, and this is the region where you can get hydrate plus water plus gas. Here you will have hydrate plus ice plus gas. So these are two situations. Suppose if the temperature or the pressure is going beyond this boundary curve, then you will not have any gas. Once there is no gas, there is no hydrate also. So whatever would be here would be just water, and whatever would be here would be gas plus ice, and this portion would be gas plus water. So this is how we define the phase stability for any given region, because these depths might vary a little bit depending upon the amount of methane available and depending upon the location, as I told, whether it is subduction zone or whether it is passive margin, and with how, on all these things it will depend. NGRA has made an attempt to somehow find the stability zone within the continental margin. So this is the Andaman region, and this is the complete Indian continental margin. This is KG region, this is Mahanadi, this is Kerala Konkan, this is Saurashtra, and this is, as I told you, Andaman. And after taking inputs from seafloor temperature and also the water column, local bathymetry, and by solving some nonlinear equations, what we can get is the depth window or the stability window for these continental margins. Going by this figure, one can understand, okay, for KG region, the gas hydrate would be stable, gas hydrate would be somewhere around 300 meter. Or for MN, you can see the, I don't know if this is visible. Yeah, you can see the depth legend here, and according to that legend, you can interpret what are the depths at which you can find the hydrate. This is very important when we handle the seismic data set, and if we find some reflector which is like gas hydrate, which is like a gas hydrate bearing layer, we need to understand that whether that reflector is coming within this depths or no. Sometimes it may happen that there are some unconformities which are also reflected in the seismic data, which also look like PSR, but going by the depth, suppose for this region, for KG basin region, if I find a reflector which is at a depth of 700 meter, definitely I'm not going to call it as a gas hydrate bearing. So before going to seismic or before trying to interpret the seismic, all we should know is whether the layers or whether the reflectors that we are picking up, are they clearly related to gas hydrate or not? To know that, we should know what is the depth window at that particular region to say that my reflector is a hydrate reflector. Now, what are the evidences? Now, once we know that there are hydrates, once you know that you also have the stability diagram with you, you have some data with you, some different kinds of data sets. What are the evidences for gas hydrates that you should look for in different kinds of data sets? So we have geophysical data sets, we have geological data sets, and we have geochemical data sets. Coming to geophysical data sets, the most prolifically used method is seismic reflections. Sometimes vertical seismic profiling is also used, which is rare. And of course, we have well logging, which is just the ground truth. Now, how will seismic help in identification of gas hydrate? Because once you have seismic section, we will study the features like perk marks, diapists, faults, all these geological features from the seismic reflections. And above all these is the BSR. Rao Saab has earlier dealt with the bottom simulated reflectors. He had told how they look like. I will show you some more evidences. But this is the prima facie, the very first thing which should occur if it is a gas hydrate reflector. Coming to geological proxies, once again, one has to understand the sediment properties, that is, which we get from cores, different kind of core studies. And then also some kind of stratigraphic relationships. That means if we know the basin evolution kind of thing, and also the gas migration. If we know these things, then we will be able to identify, we will be able to get some support from the geology as well. And then we have geochemical. Of course, this has been also dealt extensively. Although they are not very direct indicators, they do help in confirming the observations from seismic. What are the methods? Pore fluid chemistry. Whatever is there within the pore, that fluid is analyzed to understand what are the kind of ions that are there in that fluid. And of course, the gas compositions within the pore fluids. And then these two are very important aspects.
That meeting is not easy, but mine is over here.
Is there some problem? Hello?
Single chip single processor because of money. If we have money, dual processor okay, single
Hello?
Hello. Yeah, you can continue. Some disturbance is there.
Her mic is on, sir.
एक्चुअली वो से राजन से बात किया था, जिस तरह का जॉब हम रन कर रहे हैं उसमें
Nimisha Vedanti, madam, your mic is on.
Yeah, it is now muted, I think.
Yes. I
Yeah.
am muted.
The seismic, we are talking so much about seismic. Now let us understand what is seismic. There are, I hope the students know about the seismic methods. And so I will just deal with the different kinds of data sets that can be used or that are required from seismic and what are the data sets that we use. So from in seismics, there are different kinds of acquisitions and it's suitable for different settings. For land seismic, we have 2D, 3D, 3C and things like that. 3D, 3C, that is nothing but three-dimensional, three-component seismic data. Some of this has been dealt by Nisha madam earlier. Coming to, then we have the transition zones, which are like partly marine kind of environment. There we use we acquire two-dimensional, three-dimensional, four-component and two-dimensional, four-component seismic data sets. Coming to shallow waters, these are most important for us. So what are the kind of data sets that are required in these regions and what are the data sets which can be effectively used are 2D, two-dimensional, three-dimensional, 3D, four-component and 2D, four-component data sets. These are the seismic data sets which are required in this region, which will be used. Then we have something called as ocean bottom cables, wherein we have a set of receivers which are laid as a cable. Unlike the receivers which are kept in isolation over here, these are connected with each other and form a cable. Then coming to OB nodes. These are also these are different from these geophones, hydrophones in the sense that they record four-component data sets. That means you have three-component X, Y, and vertical component for seismic, and these are independently kept on the seafloor. Now coming to these are also used for gas hydrates. Yes, sometimes we use these also. Now coming to the deeper waters, these are the regions where gas hydrates will not be stable because of the high water column depth, which in turn translates to pressure, very high pressure. So under this circumstances, there will not be any gas hydrate formation. This is the conventional seismic acquisition. So we have on a ship bound. So these are the strings of receivers which are called streamers. They are tied to, they form a rope-like thing with streamers, the geophones attached. Now we have a source. Once there is a shot fired, then there is a wave propagation. These reflect the waves encounter the boundaries, get reflected, and are recorded in these receivers. So from each and every boundary, there is a reflection of the emanating waves. And analyzing the data sets which are recorded here, we try to go back to the geology and try to understand how the subsurface is. This is all about seismic. Marine seismic is no different from land seismic. It is also the same except for the equipment and equipment that is used, and that in the sense that they are all towed from the ship. That is the only difference. Otherwise, data processing and all other things are almost very much similar to the land seismic. Now, how do we identify gas hydrates from seismic? The very first identification comes in terms of bottom simulating reflector, which is nothing but a very strong reflection that occurs at the base of gas hydrate stability zone. That means beyond the base of the hydrate stability, beyond that base, there is no more gas hydrate. So this is the maximum extent at which the hydrates are stable. And then it will be parallel to the seafloor accompanied by a polarity reversal. By polarity reversal, I mean if the seafloor has got a positive polarity, then the VSR will have negative polarity. What I mean by that, I'll show in the next slide. The second proxy would be amplitude blanking. As I told you earlier, once the gas hydrates enter the sediment matrix, they seal the complete sediments. So what happens is there is no acoustic transmission, and you find a very low reflectivity. in the region. That means there is a huge reduction in the amplitude of reflections. And that would be because of the cementation effect, as I told. The third important thing is AVO, amplitude versus offset. This becomes all the more important when we are studying the free gas deposits. More than gas hydrate, if there is a free gas beneath the gas hydrate layer, then AVO is the only diagnostic which can tell us about the presence of the free gas. As the name itself says, it is the seismic amplitude and the study of the seismic amplitude versus the seismic offsets. That is nothing but amplitude versus offset. If there is free gas, we find that there is an increase in amplitude with an increase in offset. And if there is no free gas, then there will be a decrease in amplitude with an increase in offset because of the general attenuation effects. Then the fourth important thing would be fluid flow related. Once you have the seismic section with you, we will try to identify the gas migration pathways, that is the faults, then diapers, vents, and things like that. Another important attribute, another important kind of study which can be carried out using seismic data set is seismic attribute analysis, which will allow us to understand whether there is any free gas present beneath the gas hydrate layer. How do we recognize a BSR? We have a lot of reflections in the seismic section, but which reflection can you call as a BSR? These are the things that we generally have to look for when we think that one reflector is BSR. We have to check these parameters. First one is that it should mimic the seafloor. That means it should be more or less parallel to the seafloor. And then the depth below seafloor, what is the depth? This depth, as I told you earlier, this depth should match with the stability zone thickness. Then only that will be called as BSR. Otherwise, we cannot call it a BSR. Then we look for the polarity reversal and also the velocity reversal. Velocity reversal you will get only after a little bit of processing, but polarity reversal you can see straight away. Then also you need to have the reflector which will cross cut the bedding place. That means it will be cutting across the general stratigraphic depositional sequences. Then we have enhancement of amplitude, as I told you, from the AVO. Then, of course, seismic attributes. These are the two major attributes, instantaneous frequency and reflection strength, which will give an indication for free gas and for gas hydrate. Okay, now coming to, yes, maybe this is not so important. Now come to the example. As I told you, if you observe, this is the seafloor. Okay, which is white, black, and white. Now, this is your BSR. It is parallel to the seafloor. It is white, black, and white. White, black, and white. This is white, black, and white. And here what you will have is white, black, white, and black. This should be reversed to the seafloor and it should come as a very clear reflector. It should also, it is cutting across all the boundaries. You can see it is not following this depositional pattern. It has its own depositional pattern, but it is parallel to the seafloor, but it has a reverse polarity. Here the central lobe is black and here it is white. So this kind of examination should be done whenever you get a seismic section. Once you confirm from the seismic section that these are agreeable, then only you can call it as a BSR. Now, this is an example from upper to mid-continental slope regions. This is offshore US, Lake Ridge. Now, this is even clear example. This is within the middle to lower continental slope regions. So this is the seafloor, as you can see very clearly, and this is the BSR. This is black and this is white here. So it will be exactly opposite to what is there on the seafloor. And also it is cutting across all the depositional sequences. You can see deposition is going like this, but BSR is cutting like this. And it is parallel to the seafloor. Okay. Now coming to the next example, this is if there is a thrust and fold belt offshore within the continental rise. Here also you can see this dark reflection is the seafloor and the bright reflection is the BSR. You have it here and then you have it here. See, it is parallel to the sea floor, but it cuts across all the bedding planes. So that is the characteristic of a BSR. Negative polarity, parallel to the sea floor, and cutting across the bedding planes. These are the three important indications. Similarly, this is also thrust and fold weld. This is from Gulf of Mexico. Here also you can see that it is cutting across and almost parallel to the, see, it is coming from somewhere over here, almost parallel to the sea floor, but it cuts across, and here it is red, blue, and blue, and here it is, the blue is the prominent reflector. Now these are the general examples. Coming to the examples specific to India. This is in Kerala Konkan region. Again, this is the BSR, and this is, as I told, from the geological, from the seismic section, we also have to infer some geologies. So this is the general mud diaper kind of structure on the, this is from the western margin. Now this is the BSR, which is exactly parallel to the seafloor, also has a reverse polarity. This is a bright reflector and you have a dark reflector. And here you can see it even in a very nice way. And it also cuts across the depositional patterns. The next example is from the KG Basin. Now this is how it looks in the KG Basin. This is the seafloor. Okay, and this is the BSR. Here the BSR is lot more, not as continuous as we saw in the earlier sections. We also have to look at features like this, which are nothing but faults. And then we have, if we have very high reflectivity beneath the BSR, we infer that these are the free gas depositions. As I told in the earlier slides, free gas is getting trapped here. It doesn't find a way to get out from this part. It is getting trapped here. And because of the impedance contrast between the velocity contrast between the gas and the hydrate, you get all these chaotic reflections here. So any chaotic reflection which is under the BSR can be inferred to be a free gas. The first inference. Of course, we will have to substantiate it with other findings, but the first inference can be that they are the free gas deposits. Now we also have to find, we are also finding faults in this region. This is the BSR. And another important feature which I told was blanking. If you see this, this is the zone of zero reflectivity. There is no reflectivity here. Compare it with any of these regions. This part doesn't have any reflectivity. So this kind of situations make us understand that this could be gas hydrate related. Another example from the Mahanadi region. This is an extensively faulted region. Here the BSR is not very clear. But then we do find that there is a BSR sequence. It is cutting across the complete deposition. But simply because there are so many faults, there is disturbance in the BSR trace also. So when we look, I'm showing this figure because in order to show you the complications associated with seismic data, and irrespective of those complications, how we should look at the data in very, what I call very careful examination. So unless you look at these things with keen interest, you will not be able to find this reflector. So this is the reflector, which is BSR. Once again, it is parallel to the seafloor. It has the reverse polarity, and it is cutting across the general deposition sequence. Mahanadi Basin is one basin wherein this kind of faults are extensive. There are many, many faults. Coming to Andaman, this is another most promising region. Again, here it is parallel to seafloor. It is cutting across the general sedimentation pattern, and you have the reverse polarity here. So this is seafloor and this is BSR. So these are the examples from the Indian offshore region. We dealt with, I have shown you examples from Kerala, Konkan, KG Basin, Mahanadi, and Andaman. I hope now it is clear how we identify the BSR. Now, having identified the BSR, the next important proxy would be to, Yeah, the next important proxy would be to study the amplitude versus offset. As I told you, if there is an increase in amplitude compared to the seafloor amplitude, then we understand that this is the BSR which is underlain by free gas. Now, if you see here, this is one of the seismic shot gather. We are not talking of stack sections. This is the field record, I should say, NMO corrected field record. Now, if you see, the trough is the seafloor, but BSR is a peak and it is parallel to the seafloor. So this is how we identify a BSR. Now, when we plot the amplitudes of these with reference to these, we find that there is an increase in amplitude with offset. Even if you see here, the amplitude here is just this much, whereas if you go here, the amplitude is going till this far. This is just for you to appreciate and understand that this is how we look at the amplitude increase. And when we say that there is an amplitude increase from zero offset to some offset, we are finding that there is an increase within the negative polarity, underneath the negative polarity reflector, then this will indicate the presence of free gas. Coming to one real example. So this is in the KG basin, and we also have the fault. This is how we look at the seismic section. This is a full seismic section. Then once we have the seismic section, we try to identify the faults. Then we try to identify the BSR. This is the BSR, which is cutting across this depositional sequence here, parallel to seafloor. And then because of this extensive faulting, we find the trace, which is, I put a yellow line here, but beneath that yellow line, we have the BSR trace, which is a little bit less in amplitude because it is disturbed by a lot of faults. Okay, what we did was we tried to carry out AVO studies at these two locations. One is L1 and the other is L2. Both are on the same seismic profile. And we have two well logs here. Now this AVO studies can be carried out with well logs. What I showed you earlier is the seismic section. From seismic section, we infer that okay, there is an increase in offset. But if we have the well log data, we try to calibrate the well log responses with that of the seismic responses, and then we calculate the amplitudes with reference to the log. We will try to say that, okay, this is the BSR, that inference will come from the well log data. So as I told you, we have two locations here, L1 and L2, and these are the amplitude and offset plots. We just see this is the BSR. This is the amplitude plot of the free gas, and this is of the seafloor. This is of the BSR underlain by free gas, and this is seafloor. So seafloor, it is decreasing with offset as expected, but the BSR trace, it is increasing with offset. We can see that the amplitudes are moving from negative, they are going slowly towards a positive. These are at two different locations, and after analysis, we plot these amplitudes. And then we have an interpretation, which is we plot them against intercept. I'm not getting into details of AVO because this itself is a very big study. I'm just giving you a gist of what is done. Then we plot the offsets and we try to see in which quadrants these points are falling. And based on that quadrants, we can say whether that reflector, what is the amount of free gas that it is having, whether it is economically viable to get into that region or not. So there are different kinds of classes, class 1, class 2, class 3, class 4. There is a different classification for these AVOs. And once we plot the AVOs in these quadrants, we get to know which is the kind of the free gas deposit that is there. Now coming to the attribute analysis, this is again another very important property to identify free gas. So we identified the BSR, we know that there is a gas hydrate. And after knowing that there is a gas hydrate, we find some free gas deposits beneath the BSR. But whether those are actually related to gas or no, to qualify that as gas bearing, what we need to do is an AVO analysis and then a seismic attribute analysis. What is a seismic attribute? Seismic attribute, it is nothing but a property of seismic data. Any property, it could be amplitude of seismic data, it could be frequency of seismic data, it could be polarity, phase, or whatever. But this attribute is measured at one instant, and that means at one time sample, or within a time and depth window. And you can do it either on one single trace or on a set of traces. These are all various combinations which can be used. Okay, this again, an example from Andaman. This was the zoomed part which I had shown in the earlier slide. Now this is the complete seismic section from that region. I hope now all the students will be able to appreciate how the BSR looks like. It's not necessary that the BSR should be there all along the profile. It will be there at select patches. It forms, as I told earlier, it forms only where there is hydrate. Hydrate will form only where there is a pressure and temperature. So the BSR need not be a continuous feature. It would be isolated. It would be in isolated packets. So this is the BSR in this region. This is seafloor, and we find some increased reflection patterns underneath the BSR. So once we found that there were increased reflections, we wanted to see whether they are related to gas or not. To do that, we plot two important parameters. One is seismic reflection strength, or it's also called as envelope, it's called as amplitude plot, and there are many synonyms, but I prefer to call it as reflection strength. And this is frequency, instantaneous frequency. That is the frequency of the seismic wavelet at a given point of time, instantaneous at that particular point. So what it will do is it will calculate the amount of amplitude of the single wavelet and plot all those amplitudes as an amplitude plot, because these are all effectively wavelets. For each wavelet, it will calculate what is the amplitude, and it is plotting the amplitudes here. And here it is plotting the frequency. Now, what is the advantage? Free gas, if it is present, it will attenuate high frequency. It will absorb all the high frequency components. What you will be left out with is the low frequency component. So in this region, if you can see, what you are left out is with these green patches. We don't have any reds here, right underneath the BSR. You can see this portion and compare. So this is the indication. And similarly here, this is the indication which says that there is free gas, and this is the indication which says that yes, there is a BSR, and this is the indication which says that there is relatively good amount of planking, telling that this portion is acting as a seal. So this kind of studies go into an inference. Before telling that yes, this is a free gas, we have to do all these studies, and then only we can say that this is the free gas deposit. So these are major tests. Now coming to, these are all the data, these are all the actual mathematical processes or seismic steps which we encounter during seismic processing itself. Another important aspect of gas hydrate identification is in terms of geological proxies. CSIR NIO has done a lot of work in this line. What we generally do here is we try to identify the geological features. This is a kind of indirect proof. It's not as direct as BSR. We try to identify geological features, and we try to say that, or we try to find evidences wherein we can link these geological features to the free gas migration features. Like for example, we have features like this, which are faults, pipe kind of features, which are blank within, which means that they are carrying some kind of homogeneous fluid. There is no reflection whatsoever within these zones. So these are called as, these are very thin tube-like features which come up to the stability zone for any given region, and then they abruptly terminate there. These are called chimneys. Okay. And these ones, Cs, all the Cs which are there. The other important feature would be perk marks. What happens is, if these gas migration features will come up to the seafloor, what the gas will migrate through this part, it will come out of the seafloor. And when it is coming out of the seafloor, it will create a depression. And this kind of depressions, if we find the series of depressions on the seafloor accompanied by this kind of features, then we say, yes, there is some gas migration happening here. And these are also some kind of inverted structures, which are telling that there is some amount of migration, fluid migration happening here. It may not have as much strength that it will come out of the seafloor. It will come out, if it comes out of the seafloor, then it will create features like this. So this is an indirect way of telling that there is free gas migration and there is free gas present. So now, as I told earlier, this is not as direct as BSR, but yes, it does help us in understanding how the gas hydrates are coming into picture, how they are being formed, and where to look for this kind of things. And if we have a BSR which is coupled with these features, then it is like double proof for us. So given a seismic section, we look for this kind of features, we look for BSR, we look for identification of gas zones, and if they are gas zones, then we have to do an AVO study or an attribute study and then say that yes, these are the gas zones. This is the kind of research that goes into identifying a BSR or a gas hydrate. Now, what are we doing at NGRI? Let us, NGRI has acquired a lot of seismic data, both in KG Basin and in Mahanadi Basin. In the year 2010, there is extensive amount of data which is being analyzed, which is being understood. And also active areas of research, we are doing AVO inversion, then travel time, topography, waveform inversion, rock physics, effective medium theory, and things like that. These two go hand in hand in estimating the amount of hydrates that are present, amount of free gas that is present. Whatever I showed you earlier, it was to say that yes, there is free gas, but we do not know how much is there. To answer that how much, we have to do the rock physics and EMT, effective medium modeling. Now, travel time and waveform inversion. In order to do this effective medium, we need to have the accurate seismic velocities. To derive seismic velocities, accurate velocities, we need travel time topography and waveform inversion. These two are the lines. AVO inversion also allows us to understand, also allows us to quantify the amount of free gas that is present. Coming to the estimation. As I told you earlier, for VP and VS, we have travel time or waveform inversion. We can do any of these two. And also for actual in-place reserve. That means at one point, at one single location, we can do some other calculations based on the resistivity law and impedance logs. Impedance, we get impedance from sonic and density. And rock physics, then coming to the estimation, once we have all these inputs, how do we estimate? We use effective medium theory to estimate the amount of the free gas or gas hydrate concentration that is available. Now I'll quickly go through some of the, sir, how much time do I have, sir? It's already 1, I think. Anyway, I'll just quickly.
Maybe another 15 minutes.
Okay. So let us now look at the VP-VS, VP velocity determination from the seismic data. There are two kinds of routines which are done. One is travel time inversion and the other is waveform inversion. Any basic for travel time inversion, what we generally do is, this is the seismic gather. If you can see, there are various colored lines that are seen here. So we assume that these arrivals are coming from these layers. 1, 2, 3, 4. We build an initial model. And once we pick these phases, based on the phases, we say that we build an initial model, a simple plain parallel layer case model, and we generate travel times. These are the synthetic travel times which are generated from the model. And we match these synthetic travel times with that of the real travel times. These are the real travel times and these are the synthetic travel times. And if you can see here, I do not know if it is very clearly visible. If you can see here, these are the 4 color palette which I am using here. Pink is pink, blue is blue, and green and yellow. Yellow and green, I think. So these, for each short gather, we have this kind of travel times picked. And then we have the synthetic travel times which are generated from each of these layers. We match this synthetic travel time with that of the travel time of the field data. And if it matches, then it's fine. If it doesn't match, then we change the depth here of these layers. You change the depth or you change the velocity. And then again, you try to match them. If it is matching, okay, for that layer, it is fixed. Go to the next layer. Likewise, you have to do that kind of modeling for all the shots. Here we have the shots 1, 2, 3, 4, 5, 6, 7. So whatever the number of shots along the profile, you have to do this travel time picking on each of the corresponding shot gather, generate the synthetic travel time, match the synthetic travel time with the field travel time. And if they are matching, fine. If they don't match, then change the model parameters. So this is the forward modeling. And once everything is done, we just run an inversion to get the final velocity model. This is how travel time inversion is done. And once you do the travel time inversion, you get the velocity distribution and also the structural distribution of the subsurface in that region along that seismic profile. Similar is the, now using this travel time inversion, we have tried to delineate VP in KG basin. This is same seismic section which I had shown you earlier. What we do is we try to pick up we try to understand that these are the layers which are already present there. This comes from interpretation. And from each of these layers, from the shot gathers, we try to pick the travel times. You can see this, the forward model. And then we match the travel times. The black ones are the synthetic travel times, and the colored ones are the color codes. From pink color rays coming, say pink color rays are coming from third boundary, then we have to match the third boundary synthetic data set with the third boundary real-time data set. After having done this match, what we get will be something like this. This is the seismic section. This is the P wave velocities along the seismic section. For the gas hydrate region, if you see here, this is the gas hydrate region, which is at a higher velocity, say 1.9. Around 1.9 is the velocity over here, especially in this part, you can see, which is followed by a velocity which is less than water velocity, which is around 1.4, which says that this is free gas. Free gas will have velocity lesser than water velocity. This is free gas and this is the hydrate layer. Now, once you have the velocity distribution, we use effective medium theory to convert these velocities into gas hydrate saturations. I will not deal with the effective medium theory here because that is an extensive theory in itself. You will need one full presentation for that. But to understand, I'm just telling this is a theoretical method which will allow us to calculate the amount of free gas saturation if we give the VP and VS. So that is the best way to define effective medium theory. So after having applied effective medium theory with the flow to the P wave velocities, what we get is the gas hydrate saturation. So this red is the gas hydrate saturation. This is all lower saturation because there is no hydrate, 0.5, 0.9. And coming to here, this is 0.19 kind of thing. We did not do it under the free gas. We just left it at hydrate part. And because we are calculating only gas hydrate saturation, we have not done anything. We are not calculating free gas. So this is the gas hydrate saturation. So from travel time tomography or travel time inversion, this is how we come to the gas hydrate saturation. The other way of finding out velocities accuracy is full waveform inversion. Waveform inversion routines, these are slowly evolving. Rao Saab has also mentioned them earlier in the first talk. This is the basic fundamental understanding is the same. You have the field data set, you have the synthetically generated data set, you match your field data set with the synthetic data set. And if they match, it is fine. If they don't match, you change the model parameters for the synthetic data set and then try to match it again with the field data set. Now, the data set can be waveform data, travel time data, or any data. Inversion basically works on this principle only. What I showed you earlier was travel time inversion. What I'm showing you now is the waveform inversion. So these are the real-time waveforms which are converted into tau-p domain. This is the real data set. So data set at L1 and data set L2. But this example I'm showing for L1. But after having the real-time data set, this is the synthetic data set. Now we try to match these two. And we see that there is minimum error. This is your error plot. As the error plot is minimum, you see this is practically near zero error. So once you have this match within the error limit, we consider the velocity which has given rise to this kind of seismogram is good enough for this region. So I have superposed data, the real data with the synthetic. Synthetic data is on the red color, and real data is blue color. If you see, the match is very perfect. Wavelet by wavelet, sample by sample, everything seems to match. So once you have this kind of match, and then we invert for the velocity, this is the velocity that you will get under L1. That means the red color velocity is the velocity here. Okay, somewhere over here, this is how it is varying. Similarly, we have done for L2. Likewise, this can be done all along the profile. What I have shown you is a 1D inversion. If I can do it effectively at every trace, that becomes a 2D inversion. So when once you do a 2D inversion, and once you have velocity profiles like this, you can construct a figure like this. And this figure, you can again apply EMT and come to saturation profiles. So whatever the main input for calculation of saturation is accurate VP and VS. To do that, we need either to do travel time inversion or full waveform inversion. Now, the other method I have mentioned using log data. We did acoustic impedance inversion in Andaman for using the log data, which was already available there. What happens is we have the, I am sorry, there is a mistake here. This has flipped. This has flipped. Anyway, we have the log data from which we will calculate the impedance plot. And we arrive at two trends. One trend is basically different from the other, and the one that is different from the other becomes your gas hydrate trend. This is the background, and the background says your whatever deviation is there, that deviation is because of the presence of gas hydrate. So we have a characteristic equation for impedance. Using this plot, we fit this plot, and this line equation will now become characteristic equation, which will govern the impedance of that region. So using this equation, and we also have porosity log here, we try to calculate impedance at every trace, every single trace, and then we plot them. Having done this, from the impedance, we come to saturation using Archie's laws. There are Archie's laws. And after applying Archie's laws, this is the saturation that you get. So to carry out this kind of thing, you will need log data, acoustic impedance inversion and things like that, log data with seismic data. For the earlier ones, what you need is just VP with seismic data. This is the difference. Oops. So this is how we arrive at gas hydrate saturation. So there are, in a gist, if we have to summarize the complete presentation, if you have a seismic data set with you, what you have to do is first identify a BSR, ratify that it is a BSR, then look if there is any free gas. If there is, ratify that it is a free gas zone. After ratifying and understanding, then go to the modeling part, try to find out the accurate VP, accurate VS. After finding out accurate VP and VS, use them in various theoretical models. These days, there are some more theoretical models which are coming up. Of course, all of them are starting from effective medium only. There are various modifications made to that theory. So use any of those models. Then you arrive at gas hydrate saturation for that region. So to understand gas hydrate saturation, you have to start with seismic data. And that is why the title of my presentation was Role of Seismic in Gas hydrate Exploration. I think this brings me to the end of my presentation. Yeah, this is the end of my presentation. This is how the gas hydrate will look. It simply burns if you put it in the normal temperature pressure conditions. This is how it will look on the seafloor. So with this, thank you all. Thanks to the officials from university who have given me this chance for presentation. If there are any questions, I'll be more than pleased to answer them.
Thank you, Satyavani. Just I have one basic question.
Yes, sir.
Regarding the identification what you have told, Is that first you have to identify a BSR.
Sir, your
And then
audio
it is
is not
to be
very
ratified.
clear. Sir, audio is not very clear. Can you
Hello.
slowly? Maybe you
Yeah,
need
hello.
a little slowly. Yes, sir.
Yeah, please. So what I have understood from your presentation is that regarding the identification of gas hydrates, what you have told is first you have to identify a BSR, then
Yes,
you
sir.
have to ratify it,
Yes.
and then identify any free gas below that,
Yes.
and then ratify it,
Yes.
and then modeling part and everything comes next.
Right, sir. Right,
Yeah.
sir.
In my basic question is that every gas hydrate will be associated with free gas or not?
Not necessary, sir. Not always. It may, if it is a thermogenic gas, most of the time it is associated. But if it is a biogenic gas, it may or may not be associated. Thermogenic gas comes from beneath. So there is every chance that the BSR in subduction zones will be associated with free gas. Biogenic, most of the times it happens. But for thermogenic, it is almost compulsion.
Okay. If that is the case, if there is no free gas and only based on the BSR, can we say that is gas hydrates presence is there or not?
Yes, sir. From the seismic, from the BSR identification itself, we try to understand. See, every BSR will be associated with free gas, because what I'm trying to say is free gas will be there, because if there is a free gas only, you will get that impedance contrast. But the free gas will not be good enough that it will be seen on the seismic section. In seismic section, you can see it only if there is abundance. Otherwise, we will not be able to see it. So ratification of free gas doesn't come into picture. But the formation of BSR itself says that there is some gas deposition. So all the it will be there, but it may not be as much.
So the free gas may be present, but it may not be reflected on seismic section.
Yes, sir. There are instances wherein the BSR was not associated with extensive gas. It may happen that whatever gas is there, it has already been absorbed by the matrix. And there have been situations where the top of free gas doesn't coincide with the base of the gas hydrate. Unless it coincides, you will not get these enhanced reflections.
Okay, thank you.
Right, sir.
Okay, it's a nice presentation. Now, from the students' side, if any questions are there, you can ask madam and clarify your doubts, or even after that, you can give her emails. I think so. She will be ready to answer through email also.
My email is pretty easy, satyavani@ngra.res.in. You can simply send an email to that. That should be good enough.
Okay.
If there is any, feel free to write to me anytime. I will be more than happy to reply to any of the students' queries.
Yes, Dr. Satyavani Garu.
Yes, sir.
It's an excellent presentation. I actually, being from a commercial side, we have seen the angles most of the time talking about the different scenarios and attaching to the particular companies who do that and looking at the results part. But if an academician looks into those things, a researcher looks into those things, the things will be different. That's what you have presented, particularly the FWI and the TETI and other different scenes. So when we are seeing on a particular data, the things will be totally different. That's what the angle of a researcher into a commercial platform is. Totally fascinating presentation, I can say that. And the work,
thank you, sir.
Yeah, work is very, very good. And coming to the KG part, KG actually is having a good reflection scenario in the shallow, but when we go to the deep, syn rifts and thrusts are always getting into the KG deep water, wherein it is very difficult to identify the thrust and thermogenic related things. So
Yes,
mostly the concentration is on the biogenic scenario. Whereas in Mahanadi, the things are entirely different because it's extremely faulted, as you said. At the same time, the shallow level, there are so many fans involved in that. So structural scenario always disturbs the scene when looking at the gas hydrate path. The another
yes,
one,
especially identification of BSR becomes very, very difficult.
I'm coming to that because you have answered very nicely to Dr. Swami. I'm just trying to add something on that.
Yes, sir.
I have given a one word this thing that the amplitude of the BSR which is coming up is related to the free gas which is just below that. So
Yes.
many of the times what happens is the amplitude which is coming on the BSR is a indirect indication of the free gas available just below that. So in case of Mahanadi, as we have discussed, most of the stratigraphic fan related scenes and highly faulted scenario, the BSRs are not additive with the thermogenic gas below that. And even the thermogenic gas hydrates have not been established in case of Mahanadi, I feel so, to my knowledge. So like in KG and Andaman.
Yes. Yes,
So
sir.
that may be the reason why the BSRs are very, very strong, may not be very strong in Mahanadi. So it added to my learning curve. So definitely very good presentation. Congratulations to you, Satyavani Garu.
Thank you, sir. Thank you. Thank you.
Thank you, Satyavani, once again for your nice presentation. Actually,
Thank you, sir.
yeah. So on behalf of our Department of Geology and also on behalf of the students chapter, I once again thank you all the speakers. And now I request Ramesh Sri to present a formal vote of thanks to end this particular webinar. So
Sir,
Ramesh Sri.
Sir,
Yes, sir.
Swami Garu.
Yeah. Sir.
Swami Garu, just a minute. I am sorry to disturb. I am giving from SPG side. I was asked to give some things to you.
Yeah, please.
From SPG India, a message has come because of the meetings with things they could not attend. It was an excellent effort by Department of Geology to improve the learning curve of the students, and even the attendees also by arranging the webinar of this sort. Hope these efforts will continue in future, and will be happy to be a part of these efforts from SPG India. Thanks from SPG India to Dr. Nimisha and Dr. Satyavani, and which are really fabulous in covering all aspects of shale gas, CBM, gas hydrates. And lectures of this sort from eminent scholars will definitely add value to the learning curve of the geoscientific community. Efforts put up by NGRI have been well demonstrated by both the speakers. I, on behalf of SPG India, congratulate both of them, and student chapter of AKNU and Department of Geology for the excellent effort once again. And we hope that this type of webinars will be taken by AKNU in future. It's a big thanks from SPG India, and we congratulate on behalf of SPG India, the student chapter of AKNU. Thank you.
Okay, sir. Thank you very much for the nice words we got from SPG. And definitely we will continue this type of collaborations with
Sir, I would like to thank the Department of Geology, Rao Garu, for your enlightening speech on unconventional hydrocarbons in India and lighten on the horizon. And my special thanks to you, Satyavani Garu, for your elaborated talk on seismic methods in exploration of gas hydrates. And thank you, Nimisha ji, for your stimulating speech on exploration of coal bed methane and shale gas in the Gondwana basins of eastern India, and really wonderful lectures. I hope my students and scholars taken more insights from your lecture, and I hope they are very happy in the participating in the webinar. Thank you one and all the speakers. Once again, thank you.
So,
The Swami sir, continue.
yeah, please. Rameshri, please present your formal vote of thanks. Rameshri is there?
Yes, sir.
Yeah, please.
Good afternoon to everyone. Myself, Rameshri, studying from the MSc second year geophysics. Program feel happy to prospecting on the formal vote of thanks. First of all, I would like to thank our Honorable Vice Chancellor, Professor Mokka Jagannatha Rao sir, for encouraging us to organizing this webinar. I now thanks our registrar, Professor T. Ashok sir, for his continuously supporting us to all our activities. I also thanks our principal, Dr. K. Ramaneshwari ma'am, for all our support and encouragement. Now I would like to thank today's keynote speaker, Sri C.V. Rao sir, accepting our invitation and delivering a keynote talk on unconventional hydrocarbons in India. I also thank today's speakers, Dr. Nimisha Vedanti ma'am and Dr. N. Satyavani ma'am for readily accepting our invitation and delivering such a wonderful lecture on exploration of coal bed methane, shale gas of Gondwana Basin of Eastern India, and an application of seismic methods for gas hydrates in India, respectively. I thanks to our head of the department, Dr. K. Nukaratnam ma'am, Dr. K.V. Swami sir, Dr. Sudharani ma'am, Mrs. Teja ma'am, Professor Srinivas Rao sir, Dr. Peter sir, Dr. Appa Rao sir, Dr. Venkateshwar Rao sir, for taking all the pains to teach and guide us in a right direction in our academic endeavors. I thanks to all of my students who listen for both geology and geophysics program for participating in this webinar. Last but not least, I thanks our web manager, master, Dr. Srinivas Rao sir and his team to creating all the necessary links to organizing this program online. I thanks one and all once again. Thank you.
Okay, thank you. Thank you, Undal, once again. I hope
Thank
we will
you,
meet.
Dr. Swami. Thank you so
Yeah,
much.
thank you, madam. Just first
Thank
time I
you.
think I am meeting you.
Yeah,
Maybe.
we
Yeah.
spoke several times on phone. So thank you
Yeah,
very
sure.
much.
I hope similar kind of cooperation from you for our students in
Yeah.
future also.
Definitely, sir. Thank you, Rao sir.
Thank you.
Please
Thank you.
state
Ma'am.
it.
Excellent to see you back again. Okay. Thank you.
Thank you, sir. Swami sir, thank you very much.
Thank you.
Thank you. Okay.
Rao sir, thank you, sir.
Thanks, Amma. Thank you very much. Okay.
Right.
Right, sir. Sir, Vishweswara garu, namaskaram. Thank you.
Namaste, sir. Thank you very much. And we hope we'll continue to do such type of things again. Thank
Sure,
you.
sir. Sure. Can you please send that message from SPG? We'll keep it on our records.
Yeah. Yeah, I just C.V. Yadav told me to tell you because he was to attend a meeting with the director. So he told me to give on the spontaneously last I gave like that. Thank you, sir.
Oh, okay.
Thank you. Thank you.
Okay. All the students are requested to fill the feedback form so that you can get a certificate from them.
Thank you
for participation.
Okay, sir. Good night. Good day.
Okay, sir.
Bye.
Good day. Thank you, ma'am.
Thank you, sir. Thank you. Nimisha ji, Satyavani madam, thank you.
Yeah.
Thank
Bye,
you,
madam.
Thank you very much.
Nice talk.
So all the students are requested to fill the feedback form, which is given by webmaster.
Okay, sir.
And only after filling this particular form, feedback form, you have to leave. Okay.